And last but not least, we talk about the third generation, where we use novel materials. If you look at the first generation, which is silicon-based, it comes with efficiency of about 28%, which is quite good compared to the rest. But today we're going to look at dye-synthesized solar cells, which at the moment they only perform at 10% at most. So this is low compared to what is existing. At the moment, if you look at many cities, many towns, many households, they still have silicon-based solar cells. So our interest is to look at, can we look at synthesized solar cells or DSSCs? But the issue around it is the low power cells efficiency. With that in mind, we ask ourselves again, why do we want to advance and improve the DSSCs? There are reasons why they are favorable. I'll just list a few. Firstly, it's that they are low manufacturing cost. If you look at the SDG 7, we are trying to make energy affordable and accessible, and DSC has got solutions to that. Second thing is easier fabrication. They're easy to make. For those in the north where there's low light, they perform quite well. Unlike the silicon-based, which are very rigid, these solar cells are very flexible. So you can use them in very curved surfaces or in materials of fabric which are very light and easy to manipulate. So I want to just talk about the operation of a DSSC because I didn't see much of the solar cells talks in this conference. It's very straightforward. Sun's energy comes with photons. The photons interact with the dye. That's why it's called a dye-synthesized solar cell. The dye gets excited, an electron is excited and moves on to the semiconductor out through the electrode, through the outer circuit, and back to the counter electrode, and electricity is generated. In our case, today we'll be looking more around the photoanode part of this cell. The common material that is used is titanium. As you can see, titanium has got a challenge in the sense that it's got a wide band gap, and that is not favorable because it encourages a high electron hole recombination. That means electrons get excited and they recombine back, and the electron doesn't get to move across. There's a lot of research that has gone on with carbon-based materials. We have seen carbon nanotubes, we've seen graphene, and graphene tends to improve the fill factor. That's the efficiency of the photon being converted to electrical energy. However, the problem with graphene, pristine graphene, is that restacking takes place. And that reduces our PC values. So what was the aim of this project? The aim of this project was to introduce heteroatoms into our graphene structure. Pure graphene is made of carbon-carbon double bonds, and we thought if we could substitute some of those carbons with heteroatoms such as nitrogen or boron, then we could analyze and see if they could be suitable. So we made three samples, three materials. One was just basically reduced graphene oxide. And then we had nitrogen, where we have carbon being replaced by nitrogen atoms. And also we had a case where the carbon atoms were being replaced by the boron, as you can see in the last picture. So I'll abbreviate them as RGO, just meaning reduced graphene oxide, titania. The NRGO titania is just your nitrogen, where you see B, it just means boron has substituted your carbon and becomes boron-doped reduced graphene titania nanocomposite. So how did we make this? Reduced graphene oxide was made from GO. GO was made from modified Hamas method, where you just use graphite with harsh conditions of acidic nature. You oxidize it and you get GO. And then with chemical vapor deposition, we're able to reduce that to reduce graphene oxide. And the boron that you see there was also reduced in situ with the help of boron trioxide, and we incorporated boron into the structure. The last one structure there, the NRGO, we had aniline used in a chemical vapor deposition method mixed with GO, and that gave us the NRGO. And then with the thermal treatment, we were able to mix TiO2, and we were able to get our sample, which we purified and washed, and then eventually, using Dr. Blades, we were able to spread it over our TiO2 glass, and then we annealed this material, and then we introduced our dye and our electrolyte, and eventually we tested the cell. Just onto our characterization, I'll start off by looking at the SEM. If you look across from A, B, and C, we were able to see flower-like structures. And then we got to do our TEMs. What we noticed was the TiO2 clusters, and there were bigger clusters when we had the RGO, as opposed when you had nitrogen or boron doped. And then we TEM, just to measure the interlayer spacing. And we saw when we introduced our RGO, with the nitrogen or boron, the interlayer spacing was reduced. We did some FTIR, just to look at the functional groups of this material. Titanium on its own is very hygroscopic, so it will absorb water, and you'll see the peak at 3,000, 3,000 wave numbers to about 3,500 wave numbers, just water there. And then the red spectrum there is your RGO with the thermal treatment that water was eliminated. And then further on, the blue and the green, when you introduce your nitrogen, that water was removed. But what we see with RGO as opposed to the doped is that we are able to see the carbonyl peak, which are around 1670 or 1690, was also diminishing, showing us that the nitrogen or the boron was substituted in some of the carbonyls that were there. Last but not least, we are able to see the titanium-oxygen-boron bonds, or titanium-oxygen-nitrogen bonds at around 1400 wave numbers. When we did our powder XRD, we were able to see evidently there was two phases, but predominantly we had the anatase and a little bit of the rutile phase. We did Raman analysis where we look at the D and the G peak, where the G represents very graphitic carbon-carbon double bond. The D represents sort of deformed carbon-carbon double bond. And in this case, if you look at the ratio of the two peaks, their area, you're able to determine how much graphitic the materials are. And looking at the values there, the RGO gave us lower values compared to the doped materials. So the doped material sort of made the material become less graphitic. We also able to do BET to look at the surface area. What we noticed when we introduced our RGO into the titania, the surface area increased, and it even became bigger with doping. That's when we introduced the nitrogen or boron. We did some thermal analysis where we look at thermal stability of this material. Again, it's clear that when we introduced nitrogen or boron, the material became less thermally stable. But when you look at the residual amount of materials at 1,000 degrees Celsius, it was clear that the RGO, without doping, had more residual content of the TiO2, which again we'll see its effect when it comes to our analysis. So we move on to the, firstly we did some UV analysis, materials absorbed. TiO2, it's about 346 nanometers, which is not in the visible region, which is not favorable. So when we introduced these heteroatoms, the nitrogen and the boron, we saw the absorption moving to higher wave numbers, which is suitable because we want materials to absorb at visible region. We also did analysis on the energy band gap using the TOX plots. Again, we are able to see that the TiO2, which is about 3 electron volts, was reduced when we introduced RGO, and even further reduced when this RGO was substituted with a bit of nitrogen or boron. We are able to reduce that band gap, which is not favorable, which causes a lot of recombination. We were able to see through photoluminescence that the intensity of the peaks on the C graph there, the bigger the intensity means that you've got higher recombination. When you had the N or the boron, in particular the N, the nitrogen substituted, that recombination was reduced, and that can be seen from the photoluminescence results. The IV slope gave us an analysis which showed that the nitrogen doped RGO again had good electrical conductivity compared to the others. So when coming to the final results, when we did our final analysis of the power cells efficiency, we could see that we used, I didn't have data for the other dyes, but we had two dyes, Sudan 2 and ASNB. Because of time, I didn't show the other results. But ESNB produced the best results. But when you look at the efficiency, it's clear that when we move from pristine reduced graphene oxide, the top line, and introduce your nitrogen or boron, we had better field factors. That's just how much the photon is converted to electrical energy. And when we move from nitrogen to even from boron to nitrogen, the efficiency was much, much better. We are almost getting 4% efficiency. Obviously, this compared to what is out there is still slightly low, but the concept that moving from pristine material to introduction of nitrogen or boron did have a positive effect on our efficiency. So in conclusion, the titanium loading was reduced when we have boron or nitrogen, and that decreases our electron hole recombination, which is not suitable for solar cells. So having low titanium improved the optical properties. The boron and nitrogen had large surface area, meaning that you're able to apply more dye, which absorbs this light. So also the heterodoping increased the charge carrier transport, providing higher electroconductivity. Last but not least, we had better cell performance when you had boron and or nitrogen doped in our titanium-based nanoparticles. Obviously, there's a lot of work still needs to be done just to get this to above 10% efficiency. But with the equipment that we've got, with the resources that we've got, at least in principle, it shows that introducing heteroatoms could affect positively some of the materials that we use in our photoanode. With that, I just want to thank firstly Munjabulo Mgidi. She was a PhD student doing this work. She's now doing a postdoc. She was guided by then Edgar Mchweni, who is back in Zimbabwe teaching, who was a postdoc then. Also want to thank the various sponsors. I want to thank the local organizing committee for giving me this opportunity to present the work that I've presented today. And I want to thank you for braving being early this morning after a very short night to listen to my talk. I also want to welcome you to Durban. It's one of the biggest suburbs in the Southern Hemisphere. And yeah, with the lovely beaches. Please come visit Durban. Thank you for listening. I've not thought about that, but a good question, a good point. I'll assume when you move from that sheet to a quantum dot, you'll affect the surface area. Even maybe we'll get better surface areas. And that is something that I can consider. I think it's a good idea. But we haven't tried that. Because the bigger the surface area, the more you're able to spread your dye, and the more the surface area, the more the photons will interact, the more electrons are pumped out of the cell. You should be able to get better electricity coming through. But it's something to think about, yes. Thanks. Uh, Curiosity is a very important thing that we are taught. And I think it's something that we should think about because we look at nitrogen, nitrogen comes in as electron rich with those pair of electrons. Sulfur will come even better with two pairs of electrons. So it's something that you can only try to see if it works. Sometimes what you think will work can disappoint you after so many attempts and realize, no, it's not working. But it's something that one could try and look at. But remember when we substitute these things, when we remove carbon to put in nitrogen or to put in sulfur, as you suggest, you also want to think about the structure, the graphitic structure, because you're replacing carbon double bond, which has got thermal stability, is very stable, and you don't want your material to be very weak thermally also. You want your material to be functional. So depending on what atom you bring, the hybridization and the bond strength and structures has to also not compromise your thermal stability. The electronic part is the physical part of every gadget or devices. So sulfur may not, nitrogen fits well with carbon in terms of sizes in the periodic table. You look at the sizes and you move on to sulfur, again, it could be different, but again, we can only try and see what happens. Thank you.
Ladies and gentlemen, thank you for your attention. I'm going to present some part of our work in our laboratory, focus on optimization of operating parameters for the extraction of cellulose from millet husk. In Senegal, we have an annual production of millet residues estimated at more than 1 million of tons, and it's generally used for animal feed, composting, or to produce biochar. In this work, we will focus on extraction of cellulose from the husk and to find most important premise for the extraction, we will use a design of experiments. From the beginning, it's important to know exactly the composition of these millihertz to unlike if it's important or not to use this residue to produce cellulose. That's why we make this characterization. And we can see in this slide that as an ash content, we have around 95% of cellulosic contents. That means it can be good to use this residue as a raw material to produce cellulose. The cellulose extraction methodology will follow these different steps. At the beginning, we have to clean the raw materials with distilled water. After that, we have a basic treatment using adding an NaOH solution and cooking at high temperatures. And then we will have a washing step, and at last we will have a whitening step with sodium chloride. Our materials can be used in different applications, notably, especially in production of implant, production of packaging, and the application more important for us is when we use this material to in water filtration, and that's our perspective with this material. General information of design experiment allow us to see that it's a technique for evaluating the effect of multiple input variables. It's useful to clear results with favor test needed, and different steps will be made. On the beginning, it's important to postulate the model, to define the plan, make different tests, and identify different coefficients. For our model, we use the methodology of response surface to estimate effect of parameters. We will work with three factors: the NaOH concentration, the cooking temperature, and the extraction time. And as a plant, we will use the three-factor box Bentgen with 3 levels and 15 experience. Following the model, we can see that from low level, medium level, and high level, with NaOH concentration, temperature, and time, we can have 3 levels for basic treatment. 1 level we will use a concentration of 1 milligram per liter. The medium level we will use a concentration of 10 milligram per liter. And for the high level, we will use a concentration of 15 milligram per liter. For the temperature, we will have 3 factors: low level 100 degree, medium level 110 degree, and high level 190 degree. For time, we will use 60 degree, 90 degree, and 120 degree, 20 minutes. Excuse me. And following these different factors, we will have different response, and the response is the yield of extraction. We can see that for each factor, from the different level, we can see different response on the yield of extraction. And these different results can be analyzed using ANOVA to evaluate the influence of each factor on their interaction on the extraction yield. In this slide, we see the result of the analysis of interaction of the different factors. We can see that correlation coefficient of 0.98 was obtained, which indicates a very acceptable agreement between the experimental and the predictive value, because the model allows us to predict the different value, and after obtaining the value indicated by the model, we can test them on an experiment. And we see a different coefficient correlation of 0.98. For the monitored response, the difference between R adjusted and R predicted was less than 0.2, indicate that the model is valuable. Following the analysis of variance, we can see which parameter is more important in our process, in our extraction process. We obtain a p-value less than 0.05, thus showing that the model is significant, and all the factors studied, except temperature, have a significant effect on the extraction yield. And only the interaction between the interaction between NaOH concentration and time of cooking has a significant effect on the yield. The NaOH concentration is the most influenced parameter because from this factor we can see a F value of 187. Following the ANOVA analysis and focus on the interaction of different parameters, we can see that the interaction between NaOH concentration and time cooking is the most important interaction in our process. After this ANOVA analysis, it's important to analyze the optimal condition to produce our cellulose, and these optimal conditions can be obtained by design experiment, and we can see that with in temperature of 110 in an hour concentration of 5.2 and extraction time of 60 minutes, and with these three parameters we can found a predicted yield of 87%. And from there, we can apply these conditions on our experiment, and we see that we will have a final yield extraction of 87. We will have an NaOH concentration of 5, and we will have a temperature cooking of 110 with time of 60 minutes. And from there, we can say that this study successfully demonstrated the potential of Mille-Hux as a source of cellulose and cellulose acetate. Optimal extraction conditions were established, and two acetylation methods were compared. And future prospects include exploring alternative sources of biomass, optimizing process for industrial application, and developing new applications for cellulose acetate, particularly in the manufacturing of filtration membrane and environmentally friendly materials. So from this slide, I would like to thank you for your attention by giving you this nice dish from Mille. You're welcome. You're welcome. Not yet. It's on the. Is this significant? permit. Okay. Thank you for this contribution. Yeah. It's our perspective. Why we start from producing cellulose is the first step. And then after that, we will use this cellulose for another, to make another product. Yeah. Yeah.
Dear President of the member jury, dear colleague, good morning. I am Dr. Seydou. I am from Cheikh Anta Diop University, and I would like to talk about the preparation of activated carbon from olive stone and modification of its characteristics by acids, particularly phosphoric, nitric, sulfuric acid. For this, I will deal with the following plan. First of all, I start with an introduction, and I will continue with a material and method. And then I have to talk for result and discussion, and I have to finish by a conclusion. As introduction, I want to say that the development of agri-food industry generates and releases huge amounts of residues, biomass into the nature. And this phenomenon has a numerous negative effects in our environment, such as the issues of toxicity and issues of environmental degradation and issues of biodegradability. In order to tackle these issues, research trends are increasingly moving towards the valorization of industrial waste, and our work is in this context. And, and our work is in this context, and has a main goal, the valorization of a local agri-food industry waste by the preparation of activated carbon by physical activation from olive stone. Has a specific goal. We want to improve the characteristic of the activated carbon prepared by treatment with acidic agents. And also, we want to test the capacity of activated carbon in the recovery of metal, and particularly chromium iron. The figure one shows us the olive stone, which is our raw material. The table one is the elemental composition of the olive stone. From the table, you can see the major element of the chemical composition is lignite with 30.65%, and the minor element of the elemental composition is the carbon with 47.8%. These two high contents leads to the choice of olive stone as a precursor for the preparation of activated carbon. This is the material, the main material used for the preparation of our activated carbon. For the preparation of activated carbon, we did it in two steps. The first step is the preparation of activated carbon. We start by washing and blending the olive stone in order to obtain a fine particle. And after we pass to the preparation by the physical activation, and the required condition is an heating speed of 10 degrees Celsius per minute, a vapor flow about 0.1 ml per minute, and the temperature of activation is 850 degrees Celsius, and the duration is about 1 hour. After we obtain the activated carbon and we wash it until to reach the value of neutral pH, and we dry it, and we pass in the second step, which is the modification, and it's carried out by the acid bath with a concentration of 5N, and the steering duration is about 1 day. So, as a result, for the characterization of activated carbon, we have the table, the table 2, that gives us some data about the microporous structure of activated carbon. And from this, and the analysis of this result shows that the specific surface area of the raw activated carbon is about 86.4 meters square per gram. And it's essentially made up of a micropore, about more than 16%. And also the treatment of the raw activated carbon by acid agents generally leads an increase of the specific surface area. For example, for the treatment with phosphoric acid, we obtain an increase more than 30%. This is our external structure of our activated carbon. The table 3 gives us some data about the physico-chemical properties of our activated carbons. And we noted that the treatment by acid is favorable to the formation of acid function and increase it by 2 times, even 3 times in the case of the acid, the activated carbon treated by nitric acid. And also the acidic treatment decreases the value of pH 0 size. This effect can be explained by the fact the oxidizing action of the acid, which are likely to generate oxygen groups onto the surface of the activated carbon. Also, we tested the absorption of chromium ion onto activated carbon, and we noted that the acid treatment reduces the absorption capacity of hexavalent chromium, but it promotes the absorption capacity of trivalent chromium. So we can say that the acidic treatment indicates that the chromium ion absorption onto the activated carbon is hard influenced by pH 0 charge or surface function than the specific surface area. As a conclusion, we prepared activated carbon by a physical activation with a good absorption capacity of methylene blue and iodine, which indicates its structure is essentially composed by mesopore and micropore. We obtain a good absorption capacity of the prepared activated carbon for the removal of the ion chromium, about 50 milligram per gram for hexavalent chromium and 9 milligram per gram for hexavalent chromium. These values are superior or comparable to the value of the another activated carbon. And also, the acidic treatment leads to a considerable increase in the specific surface area, surface function, but decrease the pH 0 size. And this phenomenon has in consequence to reduce the absorption of the hexavalent chromium, and we have the opposite effects for the trivalent chromium. In other words, the activated carbon becomes selective with the treatment by acid. As a prospect, we want to use this activated carbon in the absorption of other chemical pollutants. Thank you for your attention. Okay. The olive contain olive for travel, from travel, yes. Yes. Okay. Stable. But after the application, I didn't repeat this elementary. I didn't repeat it. The years I don't give it, but I have the years. Yes, the years after the preparation, after it's it's not it's not high, it's low. So the years. Thank you. I did this thermograph, the test thermograph. I did it, but I didn't give it a hazard. Right. Yes, but the absorption of chromium is more common in the acid medium, and for the trivalent chromium, it's more acid for the base medium. That is why to obtain the maximum of absorption, it's required to work for the equivalent chromium in the uh, estimate. Because before we did application, we studied the optimal condition. We, it's about affinity, because in uh, wait, wait.
favor yesterday. Of a PPTF. Yeah. Good morning, everyone. I'm Dr. David Chukwebuka. I'm here to make this presentation for my colleague, Dr. Febu, who is unavoidably absent, having delay with his logistics. Thank you. So I'll be talking on the modification of low molecular weight chitosan with African arrowroot starch and characterization of the formed blend film as utility products. What are polymer blends? Polymer blends are simply chemical substance formed by the addition of two or more polymers. This polymer blend can be made either by physical mixture or by chemical combination, depending on the method you intend to use. Now, polymers are blended to enhance their distinct component traits, their physical and chemical properties. So for this project, we shall be blending chitosan, low molecular weight chitosan, which came from African arrowroot lily. We all know chitosan is a biodegradable and biocompatible, widely used in the pharmaceutical industry. The arrowroot starch is also a natural, abundant starch, renewable source with good film forming properties. The aim of this work is just to create a blend that have desirable properties for utility application. So we'll be preparing our chitosans and our starch blend with vary ratios. We'll characterize the film physiochemically and also evaluate the utility potential for biomedical and pharmaceutical application. This is just a simple method used. The arrow starch, the chitosan powder was extracted and the arrow starch was also extracted, and the blend was made by the use of this Vostes Misa. Okay, this is the result of the mechanical properties of the blend, where we had only chitosan, we had a swelling capacity of 1.9. The more we had our starch, with the swelling capacity keeps increasing due to the starch. Starch has poor retaining capacity for water, so it keeps swelling. As you can see, the swelling capacity increases as the starch addition increases. The hydration capacity, which is the capacity of it to retain water, decreases as the starch addition increases because the chitosan has a better hydration capacity than the starch. The tensile strength was also measured. The push capacity, push resistance or compression capacity was also measured. The elongation at break was also measured. Young module measured. Thermal stability measured. From the results, we can see that the blends showed better thermal stability than the chitosan alone and the starch alone. Proximate analysis was also measured, and we can see the protein content, moisture content, the carbohydrate content of the starch and the lily. Okay, this is the FTRO result of the starch and the chitosan. This is the FTRO result of the blend, where we have blend 1 ratio 0.5 and also blend 1 ratio 1. This also when we have our blend 1 ratio 2 and blend 1 ratio 4. This is the same result of our chitosan and the same result of our arrowroot lily. Surface morphology showed that same image shows smooth homogeneous structure, improved surface property with starch incorporated. When starch was incorporated, we can see some improved morphological properties and structure. This, the chitosan and the African lily at blend 1 ratio 0.5, chitosan and the African lily starch at blend 1 ratio 1.1, 1, chitosan and African root lily starch 1 ratio 2, 1 ratio 4. These are SRD results which shows that these are SRD results which show the modified blend is crystalline, indicating a new phase of blend formation. Okay, starch modified with chitosan functionality. Improve starch modified, chitosan modified with starch improves chitosan functionality, increase the structural stability, moisture resistance, and mechanical strength. Interactions with chitosan and starch was confirmed with the IRO result, and the peak shift on the IRO results indicate bond and new formation of group interactions. The scan electron microscope showed surface morphology of the film, the smoothness. Then the SRD results showed that the crystals the blend are crystalline in structure and the phase changes in the blend. Now, from the result of the mechanical properties, we can see that this blend can serve as a better excipient for tableting of drugs, and it can be used as a biomedical, it can be used for biomedical application in terms of drug delivery system, and it can also be used for packaging due to the strength, the compressibilities are high. Then we can also use it for other commercial activities because one, it is biodegradable and it is environmentally friendly. In conclusion, successful modification of chitosan with starch has been done. Enhanced physicochemical and structural properties have been seen. Impacts and future perspective, basic for new sustainable materials. This blend is basically good for new sustainable materials in various industrial applications. Further research is also needed for scalability and application testing. We want to acknowledge that fund, we want to acknowledge the local organizers, FACTS, and the Royal Chemical Society for their sponsorship. And for questions. Four, actually. Okay. Is it three sets? Okay, let me check. One. Okay. Okay, this actually for the chitosan alone and for the arrowroot lily starch alone. Noted. I'll go back to check it properly. Yeah, the SRD, the sharp peaks shows that they are crystalline. Okay. Okay, I'll go back to check. Like I said, I'm making this presentation on behalf of my colleague who is unavoidable here. Okay. Yes, we actually did different ratios, and from the results, it's clear that the 0.5 starch added to chitosan gave a better thermal stability and better results. Yes. Yeah, thank you, sir. That's part of the recommendation. Thank you. Thank you everyone for listening.
Ceremonies. C'est bon?
Ok, et ça c'est... Je peux essayer? Ça marche pas? Ah, je dois cliquer sur mon ordi. Hein? Normalement, c'est... Voilà, on met de l'autre côté. Non, j'ai celui-là. On peut mettre ici. Non, là. Hein? Ah. C'est bon. Donc ça, c'est pour défiler. Le laser, il est? C'est là, non? Ok, ça. Ok. Oui.
Good morning, ladies and gentlemen. I am Professor Jibril Fall. I am a full professor of medicinal chemistry in the Faculty of Medicine and Pharmacy of the University Cheikh Anta Diop of Dakar in Senegal. I'm also the Director of Quality Control of Medicines in the Senegalese Agency of Regulation. I'm honored and happy to chair this plenary session. Plenary session with Professor Latifa Latrous. Latifa Latrous is a professor of chemistry at the Preparatory Institute for Engineering Study of El Manar in Tunisia. She received her doctoral degree from University of Tunis El Manar in Tunisia always. Her research focuses on the analysis of micropolluents in environmental and biological samples using chromatography methods. She exhibits a strong interest in employing various sample treatment techniques, including liquid-liquid extraction, solid phase extraction, and magnetic solid phase extraction. Currently, her research is dedicated to designing reactive and functional materials for environmental and biomedical application. Moreover, she conducts both experimental and theoretical investigation into the interaction between metal ions and biomolecules, utilizing mass spectrometry to uncover fundamental mechanisms. Professor Latifa has co-authored more than 60 papers in international peer-reviewed journals. She has received several awards, including the Travel Award at the 14th Human Proteome Organization World Congress held in September in Vancouver, Canada. Additionally, she serves as an associate editor of Chemistry Africa, a journal of the Tunisian Chemical Society, published by Springer, and holds the position of General Secretary of the Tunisian Chemical Society. We will therefore have the pleasure of listening to Professor Latifa on the following term: valorization of bio-waste in analytical sample preparation. Professor Latifa, you have the floor.
Thanks, Mr. President, for this kind of invitation, presentation. Hello, everybody. So, it's my pleasure to be with you this morning. I would like first to thank Professors Modoufal and Matarsek and all the organizing committee for this invitation, which gives me the opportunity to address you. My presentation deals with the valorization of biowaste in analytical sample preparation. The first question was sample preparation. Sample preparation is the most crucial step in analytical procedure. It represents the significant fraction of the total time spent on analysis. About 61% of total time spent on analysis is about sample preparation. It is the limiting factor, since it is time-consuming and it can potentially introduce error. For example, 30% of error in chromatographic analysis come from sample preparation. No one can doubt that the best approach would be the direct introduction of the sample into the instrument. However, this is feasible only for limited application. So, why is sample preparation required, and when current samples are unsuitable for further analysis? Sample can be too dilute, that means that analytes are not concentrated enough for quantitative detection. Sample can be too dirty, that contain other sample matrix components that interfere with analysis. And the sample can present matrix not compatible or harmful to the chromatographic or column system. So, an efficient sample pretreatment is required to pre-concentration, clean up, make the sample compatible, just I said, reduction of the sample size, and to get more information from the sample and the instrumentation. To achieve all the above, analysts should apply or must apply several sub-steps such as centrifugation, evaporation, filtration, etc. Beyond any doubt, extraction techniques are the most powerful tool in analytical I continue. So, the current techniques are the most powerful in hands of the analysts. This slide, it's a bar chart of the current extraction techniques
I collected the data from SciFinder. It's the number of peer-reviewed articles on the topic keyword. So you clearly observe that solid phase extraction is the most powerful tool in hands of analytics. Therefore, green chemistry, whose, I guess, definition in 2013 recommends, among other objectives, I show here, the 12 principal objectives of green chemistry. So green chemistry recommends avoiding simple preparation. But in practice, we can't avoid simple preparation because simple preparation is necessary for analytical procedure, for accuracy results. So, and this creates a double-edged situation. For a more feasible goal, we should make simple preparation greener. How to make simple preparation greener? By achieving miniaturization, no. Okay. So, by miniaturization procedure to reduce resource consumption and using renewable resources as raw materials. Therefore, in my presentation, I will focus first on solid phase extraction and especially the performance of materials in solid phase extraction, focusing on waste valorization. The third part of my presentation, I will explore magnetic solid phase extraction and the preparation of magnetic adsorbent or nano-adsorbent and the applicability of this adsorbent in the analysis of target pollutants. The last section of my presentation will be dedicated to new sort of phase in analytical sample preparation, including octanol supported wooden tips as sustainable devices in micro extraction and cotton fibers covalently modified with polystyrene as sort of phase in pipette tip extraction. The main steps of solid phase extraction are first conditioning. So the solvent is passed through the cartridge. The cartridge is a kind of syringe made in polypropylene, and the adsorbent is fastened between upper and lower and upper threads. So when the solvent is passed through the cartridge, it wets the bonded functioning group to ensure extraction. The second step is the sample load or the introduction of the sample. So when the sample is introduced, so adsorbent pollutant are adsorbent or are extracted in the solid phase. I show here with different color and symbols the different kind of interaction. So green for strong interaction, red for weaker interaction, and in purple the not retained compound. The third step is the washing step to eliminate interferences co-extracted with the pollutant of interest. And the last step is the elution with a solvent or mixture of solvent that overcomes interaction between analytes and adsorbents. How does the analysis proceed? First, we use SPE model. The SPE model here, I show here the SPE model, is including a glass vessel and a lid in polypropylene, and the lid is capable of holding multiple cartridges. So the sample is passed through the cartridge and vacuumed under a vacuum pump. The most widely used and commercial, adsorbent are of silica, C8 and C18. I show here the mechanism of retention between and molecules, so reversed phase, we retain molecules with hydrophobic character, making molecules efficient extraction with diverse structure within the same sample. After that, we proceed to analysis, either by liquid chromatography or gas chromatography with UV or mass spectrometry detection for LC or for mass spectrometry and FIG for GC extraction. Instead of using traditional silica to extract pollutants, we thought why not valorize waste and choose this waste as absorbent in solid phase extraction. So the first idea, why not cattle bones or cuttlefish bones? Cattle bones, in French, les os sèches. So we take cattle bone powder. The powder has a porous structure with non-homogeneous and non-smooth surface. They are rich in calcium and a small amount of magnesium, phosphorus, and other elements. The XRD pattern or cattle bones powder show a well crystallized shape and the aragonite variety. So we took cattle bone powder, fill the powder in the cartridge, and proceed to the extraction of antivirals such as chloroquine, famous chloroquine, ritonavir, and indomethacin. So results, sorry. Oh, no. Results show that recovery are 98.2% with limit of detection in the range of 0.1 to 0.5 microgram per liter. However, not all raw materials are efficient absorbent, because when we try the same process with date stones and with hawthorn seeds, results are not promising. So the idea is to prepare biochar from these adsorbents. I show here the FTIR spectra of hawthorn seeds in black. Hawthorn seeds in black, and hydrochar of hawthorn seeds in red, and the comparison between two spectra, we have decrease in OH bond due to the dehydration, and decrease in CO bond to the decarboxylation. As regards hawthorn seeds are not porous. Structure is not porous. The conversion in hydrochar show a porous structure. So we applied this hydrochar for the extraction or for the removal of antibiotics. We selected two antibiotics, levofloxacin and metronidazole, from water. Recoveries are greater than 96% with the relative standard deviation in the range from 3 to 9%. Even with all of these good and satisfactory results, the use of solid phase extraction cartridge has challenges such as absorbent clogging, high pressure in the cartridge, and the time-consuming process. Magnetic solid phase extraction is a new simple treatment that overcomes traditional SPE. Therefore, in the third part of my presentation, I will focus on magnetic solid phase extraction. How does magnetic extraction proceed? We add first magnetic nanoparticles in, for example, simple water. After mix and the magnetic particles are dispersed in water, proceed to the separation of magnetic particles, magnet. Oh. Je sais pas. Voilà. We use organic solvent for the elution. Once particles are absorbed on the magnetic analytes are absorbed on magnetic particles, we use external magnet to separate. This is a short video to show you how we can separate magnetic particles using external magnet from water sample. So we selected 3 biomass sources: almond, peanuts, walnut shells, and proceed to the synthesis or the preparation of first of biochars. Then we prepared magnetic biochars using hydrothermal method, and 3 magnetic biochars are utilized for the extraction of naproxen. Naproxen is a non-steroidal anti-inflammatory saliva sample. We compare the spectrum of 3 biochars, magnetic and non-magnetic biochars. So we observe similar functional group. That means that we have the same chemical composition, cellulose and the difference is in the range, just in range and sharpness. We also observe the difference in content, and we observe also the Fe bond for magnetization. All magnetic biochars exhibit a well-developed pore structure with circular and oval pores for homogeneous sizes. And for XRD patterns, we observe cellulosic structure even after pyrolysis at 500 degrees Celsius. And we have the pattern of magnetite and hematites. In our lab, we try to optimize experimental factors either by procedure. We use one at a time approach, or even we use experimental design. And this slide show the response surface profiles of the magnetic adsorbent, for example, in terms of elution time, extraction time, elution volume, and adsorbent mass. In our group recently, we use the new software is Azurat software. Azurat software has several benefits, such as efficiency in experimental design and reduction of experimental errors. So, to analyze the isoresponse curves with the circle, with delimited, the region delimited by a circle, gives optimal conditions. We also valorize animal waste. We use snail shells, so we synthesize hydroxyapatite. Hydroxyapatite is an attractive bioceramic because due its to resemblance to minerals that are present in human teeth and bones. So we prepare hydroxyapatite. First we prepared hydroxyapatite, and then we proceed to magnetization using an autoclave. The comparison of hydroxyapatite and magnetic hydroxyapatite exhibited pores and draft structure, and it is due to the reaction between iron and calcium carbonate. And this result in the release of carbon elements and a change in structure. The XRD pattern shows significant presence of calcium carbonate and the aragonite variety, and we show here for FTIR spectra the dominant functional group on the surface. This adsorbent was used for the removal of pesticides. Pesticide from water samples. We tried tap water, water treatment plants, and river water. Recoveries are over 93.89%, with the coefficient of variation which range between 3.2 and 6%. In order to modify the property of this biochar, we think to use a polymer or especially biopolymer. So the idea to think to use starch. So we bring starch from potato peel. So potato peel. And we sensitize magnetic iron. So sensitize granite potato peel starch magnetic nanocomposite, and we use this for the extraction of ascorbic acid from fruit juice. So the XRD analysis confirmed the retention of the considered phase, and for FTIR spectra of the composite, we see the presence of the band of biochar starch on the nanocomposites. The TEM image displays homogeneous structure with pore with size between 6.3 plus minus 1.3 nanometers. Hysteresis curve gives typical behavior because the value of saturation is lower than the value of magnetite, pure magnetite. We also the hyperthermia temperature, we have 40-degree hyperthermia temperature, which releases in less than 15 minutes. We optimize parameters, extraction parameters, such as elution solvent, volume, elution time, the sort amount, and extraction time. We tested 4 types of juice, and the results show recoveries between 92.48% to 103.76, with the standard deviation not exceeding 5.7%. The last section of my presentation will be dedicated to new sorbents. And the ideas is to use lignocellulosic sorbents. So I show here the composition of wood, which is a mixture between lignin, hemicellulose, and cellulose. So the idea is to use wooden basic materials in the form of tape, les cure-dents. So we take wooden tapes, and the particularity of these wooden tapes that they have so it can host an organic solvent, for example, octanol, which shows capacity. This alcohol group increase the stability on this extraction. So we take wooden tape, we drop the wooden tape in the octanol for impregnation, Then we transferred this wooden tape in water for equilibration, and we proceed to the extraction. We transfer wooden tape in water samples, in saliva, samples, because we used this process to extract NSAIDs from saliva samples. We transfer the wooden tape in saliva samples, mix for extraction, then we transfer it again in methanol for elution, prior to LCMS analysis. This bar chart shows the difference between octanol and supported octanol and wooden tapes. So we show that with octanol we have better extraction efficiency. In fact, the retention on the lignocellulosic supports is made between part on the octanol and the wooden tape. The octanol, it plays an active role because on the extraction, and it is not considered at wooden tape conditioner. The FTI air spectra matches octanol and octanol wooden tape. Here we show the surface of wooden tapes. It contains pores, but pores are in internal pores. It's a commercial octanol wooden tape, and it is polished. That's why we can't observe pores on the surface. So octanol wooden tapes are used for the extraction of NSAIDs from water samples, and the recoveries are in the range between 18 and 140. The last example, we use always cellulose fibers, but in this time we try to modify covalently cellulose fiber. I assume that the modification, the covalent modification, is not sustainable and simple. But we use to try to make it easier. We use the click chemistry. So we the reaction between. So our anhydride is polystyrene maleic anhydride. So PSEMR will interact with hydroxyl groups on fiber, and it is introduced by this. So we use this for the extraction of 5 antidepressants from saliva sample. We take cellulose modified fiber, and we embedded cellulose fiber in pipette tape. Pipette, on prend un bout de pipette, donc une embedded wooden pipette. Then we proceed to condition. We condition methylone and extraction, and we use many strokes for extraction, many samples for extraction. And then we proceed to the analysis by LCMS. Two factors are important in amount of PSA and the time of the synthesis. We also optimize pH, ionic strength, and the number of strokes. Before concluding, we will give you an overview of our lab. We have 3 groups or 3 teams on our lab. The 4th group is dedicated to the synthesis of novel environmentally nanomaterials, and we investigate catalytic performance of heterostructure oxide. We apply this for surface phenomena. The second group is TRACES, which I'm leader of TRACES group, and we try in this group to bring a comprehensive approach to analysis from sampling and sample preparation through chromatographic separation, identification, and quantification. The third is dedicated to thermal, rheologic, and morphologic analysis. I also take this opportunity to invite you to submit and set Chemistry Africa of 2.3. I'm General Secretary of Tunisian Chemical Society. I invite you to attend and participate Tunisian Chemical Conference, which be held in Hammamet from 15 to 18 December. I know that registrations are closed, but we can make a last but no least, I would think it's important to thank the group behind the work, so my co-workers, colleagues, and students, my collaborators, and obviously you for your attention. Thank you.
Thank you very much, Professor Latifa, for this interesting presentation and the valorization of all these materials. If you have question, Professor Osman Diouf, you have the floor.
Voilà, je vais utiliser celui-là.
Thank you for your presentation.
Welcome.
But I would like to ask you for the magnetic property for your nanoparticle composite.
Yeah.
Because I think that you obtain the product using iron.
Yeah.
And what type of technique you use for studying the magnetic property?
So we take iron 2 and iron 3. So we try to sensitize magnetite through hydrothermal methods. And we check the magnetization either by hysteresis curve.
Because if the curve I have seen that there is no hysteresis.
I show one hysteresis curve because I don't have time to yeah. I show one hysteresis curve. Okay, thank you.
Another question?
Thank you, Latifa, for this very nice and informative talk.
Thank you.
I have a question about magnetic nanoparticle. How you prepare that? Which size at the end you get? And how you modify it? And are you sure that when you use external magnet, you recover total magnetic nanoparticle?
We start by the preparation. First, it depends on the method. We try two methods. We prepared for the first method. We prepared first biochar, and then we take iron and we mix iron with biochar, or we put all together in the same autoclave and we prepare.
It's only by absorption or something like that. Okay.
Yeah.
Are you sure? How about size? You're not sure about size. If it's nanoparticle or not?
Yeah. We tried always 10. And for example, I show the example. We have obtained 6.3 nanometers by size.
It will be difficult as colloidal when you use external magnet. Difficult to get all
we try to use
a strong magnet.
A strong magnetic here.
Yeah, I understand that.
But we have always traces of particles in.
But this is impact the recovery. That's what I mean.
Yes.
Thank you.
So we have to evaluate this.
Okay. Thank you.
Okay. Thank you.
Last question.
Thank you for your talk,
Thank you.
Professor Latifa. I just want to know, because you use like many kinds of materials, you use wood, you use catfish, and you use another kinds of fruits. So the question, how do you think of using those kind of materials, and why do you choose the kind of material?
Okay. So the goal is to valorize bio-waste. Okay, this is the first goal. And it depends that what we have, the abundance, for example, waste, etc. So first, for example, we try cattle bones, shell nails, because they are, we found this with a huge amounts in nature, so we try to valorize these materials.
Thank you.
Thank you.
Okay. Thank you so much.
Thank you.
Thank you so again, Professor Latifa. Okay. Next state, President.
Merci beaucoup. Ok, waaw dama lay. dafa mel ni est-ce que dañoo war a ndekki dafa mel ni jeex na pause la waaw pause la après première rek la quoi après première d'accord.
Okay, so you have a USB. Okay.
Yes.
Okay.
It's easier, I think.
Oh, way easier.
Yeah.
It's, I have to.
Oh no.
This one is the power for
Oh, I see. Yeah.
it's the HDMI, the Wi-Fi cable, so it powers itself with the USB.
No. I'm just getting my presentation on the computers. So I keep.
Which one? This one?
Yes, the bottom one. Yes. Yeah, but that's it. So once it's on, I can sort of just look at it and go, yeah, that's what I need to do.
So it's
Ça va bien.
oui, ça va.
Très bien. C'est lui qui présente après.
Non, c'est le
No,
professeur.
I'm not first, but
Ah, ok, c'est vous qui présentez.
Ouais, je suis venu.
Excusez-moi, je n'ai pas compris. Vous devez présenter. Vous avez votre présentation sur clé. Donc, il faut juste nous la donner.
Nous sommes deux, hein?
Ah, vous êtes deux?
Ouais.
Merci, sir.
We go into day 3,
Day three.
document is
Yeah.
Assemblée Générale.
Somebody's going on day 3. Okay.
Donc ça c'est moi ma présentation.
Oui.
Donc lui, il demandait est-ce qu'il utilise sa machine ou c'est la même machine qu'il veut.
Bon, il peut utiliser cette machine.
Voilà, il va venir vous le dire s'il faut. Vous mettez dans une clé et puis vous mettez sur la machine aussi.
C'est Dakar face. Donc le document c'est Assemblée Générale. Day 3.
Non.
Ok. Si vous venez dans ce document,
Ouais.
vous allez à day 3.
Je vais à day 3, d'accord.
C'est là on va
D'accord.
ouvrir, quoi, quand vous allez venir.
D'accord, ok.
Donc lui, vous avez dit qu'est-ce qu'il doit faire, qu'est-ce que dans votre clé USB.
Ok. Maintenant, je vais le voir parce qu'il est là-bas assis. Je vais lui demander. Soit il vient avec sa machine. Pour sa machine, il n'y aura pas un problème. On ne perd pas beaucoup de temps.
C'est ça le souci.
Ben non, il n'y a pas de souci. Il faut dire ce qui est. Oui, il faut dire ce qui est efficace.
En général, on préconise les clés USB.
Oui, mais il faut le faire maintenant parce que pendant qu'on est en pause.
C'est qui?
Attends, on va plus belle.
Can you just escape this one? Escape.
Oh, you want to get out of this?
Yeah. Escape.
What's that? That's a meeting?
Can you just stop this one?
Okay, let me see.
No.
Look like that's a video.
Yeah, I don't know why it's not.
Okay. So why can't I see?
So I want this one.
The second one, test.
Okay, which one is
No,
it?
no, not delete. This one. That one. That's the PowerPoint presentation. It's fine.
Okay, so that's that one.
This one I didn't delete. I can delete. So that's it.
Okay, so you want to copy it into the computer?
This one?
Yeah.
Yes.
You want to copy
But,
it?
yeah. I don't mind. I can have that.
Okay.
Yeah, we have that one. No, that's fine. I can have this. What I want is the video copy into the computer.
Okay.
Can you see if the video works?
Okay, so you want to present through the USB key. You don't want to use the computer.
Okay, we can copy.
You can copy, but it's a code of the two documents. Okay.
Let me see. Senegal Exufor. So that's it.
No, this one we need to copy this and that.
Okay.
Maybe I'll delete it for
I
you.
don't know what happened with the mouse, but I can just see it. I can just see it. They might have touched one of the on the keyboard. There's a button for that. I just can't remember which one is it. Oh, this is powering this up. It powers this. Okay, so we can copy it. Anyway.
We just want the first one. Put it as one folder, but it's two things. You don't want to search for them anyway. Put a folder. Can you create a folder? Instead of a file, put a folder.
Sorry.
It's just the mouse is not working. Maybe restart the laptop.
What will it be called?
Two things that we showed you.
This one?
So I call it presentation. Should I put a name on it?
RSC.
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 Yes. So you put that one there, and this one there.
And just if the video works.
Now the mouse up here. Okay, can we check the video, please? The video is that one. But how can we?
Oh, you want the sound from this one?
Yes.
Yeah, you should have told us earlier. So we'll have to do another thing to do. Maybe we can take the video and put it in the other computer over here. So we can start it from there. Then you will have image and
that's
sound.
fine. That's fine.
You can have image and sound.
So my presentation starts with this, and then it's a do, right?
Yeah, exactly. It will be easier for us.
Yeah. So you can transfer that to the.
Exactly. So what I will do is going to.
Because they unplug that thing.
Sometimes there are modes of display. When it's on.
When it's overwhelmed, just do it. Remove the slides and just point enter.
Oh, you can do that.
Because they need to have.
Well, you can ask around for.
It's easier to stand here because that microphone out.
Yeah. So I'm taking.
Otherwise, this is
That's
on.
it.
My life is here.
Okay, we're going to take good care of it. Don't worry. Okay, so you can go there so they can copy the video. You can show.
Yeah, I just don't know it's somewhere. I don't know where it is. Vincent, where is the presentation now? Yeah.
It's here. Assembly, the whatever. Open them. Open, open. Open. And then it goes to days, day 3. We're on day 3. That's ours, yeah. Put yours there. No, just add it there, it's easier. And just put your name.
Is that yours? You can close it.
Close it. Just copy it from, yeah, day 3, just drag it into there. Yeah.
Hello,
Yeah, that's it.
I'm Martin
And that's
Polyakov
ours
from the
there.
University of Nottingham.
Yeah.
So we can actually
You can put your name if you want.
Bonjour, je suis Zakaria Samara,
Just
du
write,
Conservatoire
right
national
click
des
and
arts et
put name or
métiers.
something.
Bom dia, sou Ana Aguiar Ricardo, da Universidade Nova de Lisboa.
And we're here to tell you about the 13 principles for greener Africa.
Nous sommes là pour vous présenter les 13 principes de chimie verte pour une Afrique plus verte.
Estamos aqui para apresentar os 13 princípios da química verde para termos uma África mais verde.
So,
What is it?
Maybe it's
What are you looking for?
13 years ago, some African colleagues published
Donc je vais me présenter d'abord, après Ousmane Nguyen moo du ko introduire. Bon, man nag kii bi c'est en français bi. Thank you so much. I'm happy to chair this session. Your attention, please. We are now for the next session. In this session, we have two presentations with Professor Kurfia Jawara and a second with Mr. Usman Koulibaly. Professor Kurfia Jawara is a full professor of outstanding class university and Knight of the National Order of the Lion in Senegal and honorary president and foundation member of the African Member Society. Membrane Society. He is vice president of Senegalese Committee for Chemistry. He is a former university rector of Ziguinchor and chairman of the organization committee for the first international conference in West Africa on membranes, water, and health, and chairman of the Third International Congress of the African Membrane Society. Last but not least, he is the winner of the CEDA 2010 Award for Innovation in Desalination and Defluoridation by developing a new fluorine removal and desalination process coupled the solar energy for drinking water. Professor Kurfia, you have the floor.
Thank you so much. Thank you very much. Good morning, everyone. I'm going to talk with you about reverse osmosis and scientific issue for seawater desalination in Africa. We are about to present. In my hand, I just present the academic issue, for around membrane technology for desalination. In West Africa, we have 16 countries, and most of them are faced to the sea. And at the same time, people face to water scarcity and a lack of drinking water quality. Near these countries, most countries who are faced to the sea, you have also the other country when we can find rivers such as Niger, Lake Chad, Senegal, Gambia, all drain across border watershed. So we can see that in West Africa, states are interdependent in terms of water resource. The estimated people should reach 796 million inhabitants in 2050. So it will be very important to think about access to water quality, especially to drinking water. And we know that between 40 and 60% population in West Africa remain concerned about access to drinking water and also water sanitation. For drinking water, we have to know some parameters. Some parameters like microbiological parameters, organic, organoleptic, physicochemical, and other elements. But it is important for chemists to get physicochemical measurement like hydrodynamic total, alkalinity, salinity, turbidity, and strong acid salts. The heart of desalination, in the heart of desalination technology, we use membrane. A membrane, for us chemists, we know that the nature of membrane, you use molecular and polymer like polysulfone or polyphenylsulfone or polyether sulfone, like that. And also, you see the possibility of molecular that for cation exchange or anion exchange. That we can see here an example of membrane. It is very important to know in desalination technology, the heart is the membrane. The membrane is the operating one, and we have to have knowledge in membrane technology. So that's an example of the membrane. We can see better. This is you have at the top the layer of the membrane, polyamide membrane. It is an active layer, and after you have the polysulfone and polyester support. It's a macroporous support. In reverse osmosis mechanism, for osmosis, direct osmosis, we have a transfer of solvent to concentrate areas. In reverse osmosis, we have to apply a pressure to have that the transfer of solvent from the concentrate area to diluted area. That's the principle of the mechanism of reverse osmosis. So that's why if you operate in reverse osmosis, you have to need pressure, so enough energy to do it. You can see here in reverse osmosis membrane, the reverse osmosis membrane is in the field of high pressure, need high pressure. So all this macrofiltration, ultrafiltration, nanofiltration are also membrane technology. But for desalinated water, for desalination of sea water, we need to use reverse osmosis. That's just a quick operating model. You see the feed, when the feed into to the membrane, you have a permeate is the filtered water, and the concentrate is the rejected water. So it is important to retain that we need at least an osmotic pressure. Osmotic pressure for seawater, where concentration is around 35 ppm, you have to have an osmotic pressure and to apply a pressure higher than osmotic pressure. That's parameters. And parameters interesting here, you have to know the productivity or the efficiency can be calculated. But it is important to retain the conversion rate. The conversion rate gives you the yield you can have when you do a desalination. And desalination, the yield is very important because you have many sorts of membrane, and the choice of the membrane, your yield can depend by your choice. This is just an example of membrane. You have hollow fibers or tubular model. That's you see your feet come around inside of the membrane, and the layers that the active layer filter the water, and you get your permeate through the membrane. But we have to retain that in desalination, we don't use hollow fiber or tubular model. In desalination, we generally spiral wound. Spiral wound are more adapted to seawater desalination. And so this is a mechanism how we can prepare spin wound membrane. You have the collector at the middle, and the collector is the part where you can collect all the filtered water, all the permeate. This is Mario. You have to see, this is a spiral wound. In this spiral wound, it is important to see that the permeate comes from the collector at the middle. So when the water, your feed goes through membrane, you have between membrane, you have something which we call spacer. The spacer to help to avoid something of flaring. When you do this filtration in desalination, sometimes we need to go on a second floor. Why? Because all salts are not reactive. You have some elements who are not reactive. You need to put another state and to this is an example of membrane, seawater membrane, where at the first step we don't eliminate all salts. We eliminate much more salt, but particularly one element can be. I speak about the case of boron. I think
generally it is around 45, 40, 45, or 50 for the operation. But when you have one state, you see that with 45, you have to lose much water. Your feet around the important part of your feet is frozen. So you have to use another state. It says, so see, as the first stage, you recover 47 of your. Okay, see, as the first stage, you have 40% of conversion rate. He said that, okay, so the rejected water can be improved again with the same conversion rate. At the end, we have 85% recovery. But we can't, in one stage, we can't work at this recovery rate. So in the yearly, it can be important when you have many stages. That's something which is improved in the lab, and we have to recommend it. Now you can know that the development of desalination system is partly due to the maturity of membrane projection software. You have many decisions, many software to allow that to know at first what with your water quality, what's the best condition of operating for your reverse osmosis system. But this information from osmosis must not in no way replace pilot scale test and the opinion in the final choice of membrane. The final choice of membrane is very important. After simulation, after visual software, after study, theoretical study, you have to choose the best choice of membrane. All membranes don't have the same results. This is an example of a plant of desalination, and we see that in around the world, we have 6 million cubic meter per day, which is produced by membrane. So it's very important, and we say that it can be very helpful to know that in West Africa, countries face the seawater can improve the technology for drinking water for the population. can reduce 6 lakh for battery. You don't have 10, you have a good water quality. And the space is less than 10 to 20% than the operation, the conventional. This is also a specific of desalination. You see that in desalination, what is more expensive is the building. The building of desalination plant is expensive. But this but more important in this slide is to repair and to see that in seawater concentration, salt concentration, you have to work in this pressure, but you have to see the conversion rate is not so high. And we see that if we are in this conversion rate, we have to use more stage to have, if you want to have much more permeate, much more drinking water. Desalination can be done also in brackish water, but in this case we speak about seawater desalination. But it's important to know that that brackish water we can do desalination, it will be less, more or less expensive. So for this, we speak about it is important to know that if we want to go towards a desalination plant, it is important to train technicians, especially in desalination plant, water reuse. Our states in West Africa are going towards the desalination plant in our states. But we don't know that, we don't see that school when we can try to young students for desalination. We think that it is important to have rigorous monitoring to build regional institute or camp of training of this technician. Also, we have to think, we have to talk now what the become end of life of mankind. When you use desalination, at one time your membrane will be dead. What we do? We throw it to the environment? No, what we can do? This membrane, dead membrane, can be removed for processing. So it is important that water companies, to work with university to have a strong partnership with university officials of land. And we see that these two recommendations are very important for our government, for our companies in working in water field. So we hope that, let's hope together that desalination will make it possible to anticipate the drinking water needs of population instead of being a building system. Thank you so much.
Thank you so much, Professor Ofia. The certain part of the presentation will be done by Mr. Kulibali. Mr. Kulibali, I will summarize the profile. Is an hydraulic engineer, has built
experience that is resistant to the problems of access to drinking water in Dakar agglomeration and other regions of Senegal. After obtaining a master's degree in physical science at the Cheikh Anta Diop University in Dakar in 2001, his academic career was sanctioned in 2005 by diploma engineer in rural equipment, hydraulic option from École Inter-État Rural Equipment at Ouagadougou in Burkina Faso. His work as project manager between 2008 and 2013 is took of action to mapping sanitation project and various other areas over the course of capacity building. Here is the summary of the profile of Mr. Fulbari. Fulbari, you have the floor. Thank you. The communication will be done in French. No.
C'est dommage pour les non-francophones. Bon, merci. Donc, il m'avait offert la présentation de notre projet de désarmement.
Notre professeur Kourfia Diawara. Donc, je m'avais vous faire la présentation sur le projet de dessalement que nous sommes en train de réaliser actuellement au niveau des mamelles pour essayer de résoudre la problématique de l'approvisionnement en eau de Dakar. Donc, comme plan de présentation, déjà, je vais essayer d'expliquer aussi les ressources en eau qui alimentent la région de Dakar. Pourquoi on a opté pour le dessalement au niveau de Dakar, comme l'a expliqué le professeur, parce que Dakar est sur une presqu'île. Donc, l'usine de dessalement de Mamelles, pourquoi on a choisi l'implantation au niveau des Mamelles, des informations techniques aussi sur l'usine de dessalement, les problématiques qu'on a eues sur le bord pendant la phase d'exécution et quelques résultats de simulation et les mesures environnementales et sociales qu'on a optées pour essayer de mitiger un peu les impacts de l'usine avec les rejets, les études qu'on a eu à mener pour essayer de mitiger, de circonscrire les impacts sur l'océan, sur l'environnement marin. Donc, comme vous le savez, Dakar représente presque 0,3% de la population du Sénégal, qui regroupe les 22% de la population sont concentrés, pour dire qu'il y a une forte démographie à Dakar, avec une forte pression en tant que nous, société d'eau, pour alimenter ces populations-là. Et comme seule ressource qu'on a pour alimenter, pour l'alimentation de la région de Dakar, c'est le lac de Guerre, qui se trouve à peu près à plus de 250 km. À plus de 250, le lac de Guerre, qui se trouve à plus de 250 km de Dakar, où on a des usines qui traitent l'eau et l'acheminent jusqu'à Dakar. Donc, pour dire que, en plus de ces usines qu'on a sur le lac de Guerre qui est alimenté par le fleuve Sénégal, donc, en plus de ces usines qu'on a sur le lac de Guerre, on a des batteries de forage qui contribuent aussi à l'alimentation de Dakar. Donc, en termes de, sur les 600 000 mètres cubes jour qu'on a au niveau du lac de Guerre, presque les 58% viennent du lac de Guerre. Donc, pour montrer la forte dépendance de la région de Dakar par rapport à cette source d'alimentation. Lorsqu'on a fait notre schéma directeur pour l'alimentation en eau de Dakar, en 2013 déjà, toutes nos usines étaient presque en saturation. Et donc, il y avait déjà, les usines étaient en transfert. À cela s'ajoute aussi l'incidence qu'on a eue en septembre 2013 sur l'usine de Lac de Guerre, qui a privé Dakar presque 2 semaines, une bonne partie de la région de Dakar, sur 2 semaines avec une coupure d'eau sur près de 2 semaines. Donc tout cela est aussi, de plus en plus, on voit que les forages au niveau de Dakar, il y a une forte salinisation. Ça veut dire que compte tenu de l'exploitation minière que nous faisons sur ces forages-là, donc de plus en plus nous perdons nos forages parce que les forages sont en train de se saliniser. Et en plus, il y a, étant donné qu'il y a beaucoup d'agro-business qui se développent autour du lac, on a eu une forte pollution aussi sur le lac. Donc pour dire que l'alimentation en eau de Dakar, qui est fortement dépendante de ce lac, devient de plus en plus problématique pour nous. Donc il nous fallait chercher, il nous fallait diversifier ou bien chercher d'autres ressources pour alimenter Dakar. Donc c'est pour cela, déjà, il fallait qu'on réduise la dépendance de l'alimentation en eau de Dakar par rapport au lac. Et avec l'investissement qu'on devait faire compte tenu de la population qu'on aura, les projections qu'on a en 2035 qui montrent qu'il fallait qu'on fasse des investissements pour augmenter la production, pour alimenter Dakar. C'est ça qui nous a amené, compte tenu que Dakar se trouve presque sur une presqu'île, de réfléchir sur le dessalement de l'eau. En fait, ça nous permet de diversifier et de sauvegarder aussi nos forages. Donc, pourquoi on a choisi à implanter l'usine de Dakar au niveau des Mamelles, où on avait de sérieux problèmes d'espace au niveau des Mamelles, parce qu'on a eu à mener plusieurs études qu'on va voir plus tard, qui nous ont permis d'installer l'usine ici. En plus de ça, l'usine est très proche de nos réservoirs qui se trouvent à côté, où on a 35 000 mètres cubes jour qu'on stocke au niveau de ces réservoirs-là, qui sont juste sur le pied du monument des Mamelles, où on a presque 35 000. En plus de ça, au niveau de ces monuments aussi, on a la proximité de l'alimentation électrique de la boucle 90 000 de Sénélec, qui est une alimentation sécurisée. Donc, c'est tous ces paramètres-là qui nous ont amenés à implanter l'usine de dessalement au niveau des Mamelles. Les composantes techniques qu'on a sur l'usine, comme vous le voyez, excusez-moi. Donc, au niveau des Mamelles, étant donné qu'on avait un problème d'espace, donc l'usine a été scindée sur plusieurs parties. Ça veut dire que déjà, à ce niveau-là, il y a l'usine de traitement que nous sommes en train de réaliser à ce niveau. Mais à ce niveau, on est sur une falaise de 30 mètres par rapport à l'accès à la mer. Et le seul accès qu'on avait à la mer, c'était au niveau du rond-point des Mamelles, où on a un accès à la plage. Donc, la station ici, on a la station, la prise d'eau qui est ici. Donc, on a la station de pompage de l'eau de mer qui nous permet d'acheminer l'eau de mer jusqu'à l'usine. Et une fois que c'est traité, en violet, en vert, on a les rejets qu'on rejette en mer. Donc, la partie rejet des saumures et prise d'eau se trouve sur cette partie-là. Et l'autre partie, on a l'usine de traitement avec l'ensemble de ses composantes, où on a le pré-traitement, l'osmose inverse qui se trouve sur cette partie-là, et la station de pompage est à ce niveau-là. Il y a le raccordement électrique qui est au niveau du monument des mamelles et l'évacuation des saumures qu'on voit ici. Donc, pendant la phase d'appel d'offres de conception de cette usine, on a eu à mener des campagnes de mesure de la qualité de l'eau pour pouvoir bien dimensionner, comme le professeur le disait, la qualité de l'eau est importante pour pouvoir dimensionner les membranes et pouvoir dimensionner l'usine. Donc, on a eu à faire des campagnes de mesure de 2016 à 2017 sur une année, où en balayant l'ensemble des saisons de l'année, qui nous ont permis de fixer les paramètres de l'eau brute, où on a les paramètres en termes de TDS, en termes de température, en termes de pH, oui, et en termes de pH, et tout ça qui nous ont permis de fixer les paramètres à l'entrée de l'usine. Une fois qu'on a fixé les paramètres à l'entrée de l'usine, donc avec ça, on a dimensionné le système de pré-traitement, pour avoir la qualité de l'eau qu'on veut à la sortie. Donc, en termes de pré-traitement, on a fait une innovation sur ça, parce qu'étant donné que lorsqu'on a fait des mesures, on avait détecté de l'hydrocarbure en 2016-2017, une forte quantité d'hydrocarbures sur l'eau de mer. En 2018, lorsqu'on a repris ces campagnes-là, on n'avait plus d'hydrocarbures. Mais néanmoins, dans le dimensionnement de l'usine, on a tenu compte du traitement de l'hydrocarbure en cas de pollution ultérieure. Donc, c'est pour cela qu'on a utilisé des flottations à air dissous et aussi du charbon actif qu'on va injecter en cas de pollution d'hydrocarbures. Et on a 5 trains de membrane pour la première phase, et la seconde phase, il y aura 5 trains. Le taux de conversion qu'on a opté pour cette usine-là, c'est 45. Et aussi, on a opté d'utiliser des échangeurs de pression pour économiser aussi sur l'énergie. Et enfin, maintenant, on aura un système de traitement. Donc, c'est la qualité qu'on a à la sortie, qu'on veut avoir, qui est garantie, qui sera garantie par le constructeur à la sortie pour l'eau traitée. Maintenant, pendant la phase de conception, on a eu quelques soucis sur la qualité, on a eu quelques soucis sur le taux de bord. Lorsqu'on faisait les analyses en 2016-2017 avec le laboratoire Orofin, on avait un taux de bord de 4,2 mg. C'est ça qu'on avait exigé, on a arrondi à 5 mg. C'est ça qu'on avait exigé au constructeur pour dire que la qualité de l'eau à l'entrée. Mais lorsqu'on faisait nos études, on s'est retrouvé avec des qualités, avec un autre laboratoire, on s'est retrouvé avec des qualités plus élevées, qui mettaient en cause toute la partie conception de l'usine. Donc, il fallait qu'on trouve une solution pour qu'on puisse garantir à la sortie un taux de bord qui est à 2,4 mg, qui est conforme aux recommandations de l'OMS. Donc, on a eu quelques soucis et on s'est rattaché des services de l'université et de laboratoire de l'ESP et de laboratoire de l'hydrochimie qui nous ont permis, où on a fait encore des analyses, et donc on s'est rendu compte que les taux élevés qu'on avait, c'était juste des taux qui étaient liés au protocole d'analyse que les laboratoires ont utilisé, qui nous ont confortés. Mais néanmoins, on a essayé, dans la conception de l'usine, de tenir compte de cette éventualité de taux élevés de bord. C'est pour cela que sur le choix des membranes, on a choisi des membranes, sur la conception, on a choisi des membranes qui ont un taux de rejet plus élevé par rapport au bord et d'autres qui, pour mixer, pour avoir un taux de bord moins élevé à la sortie, pour pouvoir respecter. Donc, ça, c'est les résultats des simulations qu'on a eu à faire en fonction des températures avec un taux, en prenant le cas le plus défavorable, un taux de bord à l'entrée de 6,5. Et maintenant, suivant les pH, on a fait avec plusieurs températures, voir est-ce qu'on va respecter la qualité de l'eau à la sortie. Donc avec 6,5, il n'y aura que juste pour les températures de 30 degrés où on aura un taux qui est un peu élevé par rapport au rejet de bord, où il faudra aménager quelques dispositifs constructifs pour pouvoir rester au niveau de la norme. C'est pour cela qu'on on doit mettre en place un dispositif d'injection de soude pour pouvoir traiter en cas d'élévation et la température pour pouvoir traiter ces cas de fumée. Donc c'est ça qui nous ont un peu conforté dans notre conception. Tout ça, c'est les résultats des simulations pour montrer. Donc si en termes environnementaux, on a eu toutes ces étapes-là qu'on a eu à franchir jusqu'à ce qu'on puisse avoir notre certificat de conformité environnementale pour pouvoir réaliser l'usine. Et en plus, on a fait des mesures, des analyses, des simulations par rapport au rejet pour voir l'impact du rejet par rapport à l'environnement marin. Et on s'est rendu compte qu'on est une fois que le rejet, si les saumures sont rejetées en mer, à 18 mètres de l'hémisphère du rejet, on est presque aux mêmes caractéristiques chimiques que l'eau de mer. À entre 25 et 20 mètres, les concentrations sont divisées par 25 à 20 mètres. Donc, ce sont ces simulations qu'on a eu à faire pour pouvoir implanter le point de rejet à la suite de nos études de courantologie et de baltométrie. Donc, ça, c'était les audiences qu'on avait fait au niveau des populations locales, parce qu'il y avait une forte résistance des populations locales pour pouvoir implanter. Donc, on a eu à faire des visites, on a eu à faire des réunions, on a eu à faire des visites de benchmarking pour pouvoir expliquer aux populations que l'usine ne sera pas, ce sera zéro impact, mais l'impact sera maîtrisé par rapport à l'expérience qu'on a sur ces genres d'usines.
Merci beaucoup, M. Koulibaly. Malheureusement, on est très en retard sur le temps. C'est tellement intéressant, mais voilà. On aura donc des discussions dans les couloirs. One question? Next speaker. One question. And next speaker. Yes. So.
Est-ce que vous avez fait un sondage de terrain et voir s'il y a des nappes phréatiques riches, je dirais, en débit et en qualité de l'eau de l'océan pour éviter un peu le des bords ainsi? Est-ce qu'on n'avait pas parlé de ça? Vous avez compris? C'est-à-dire, vous avez fait un sondage, vous avez vu des nappes phréatiques riches, des forages, où on peut avoir de l'eau sans passer par l'océan? Oui, même si l'eau est saumâtre, mais au moins vous évitez le problème de bord ou quelque chose comme ça.
Un espacement qu'on doit respecter. Donc dans cette zone-là, on n'a pas assez d'espace. Et compte tenu de la quantité qu'on veut, on ne peut pas mettre des forages côtiers parce qu'on est dans des usines qui est à 100 000 m3 jour, 100 000 à 50 000 m3 jour. Donc on ne peut pas faire des forages côtiers dans ce genre d'usine.
D'accord. Dernière petite question. Est-ce qu'il y avait un traitement post-traitement plutôt de l'eau? L'eau qui est récupérée, il n'est pas potable peut-être, il n'est pas. Est-ce que vous avez ajouté d'autres éléments, quelque chose comme ça?
On a du CO2, je ne sais pas si je l'ai montré, on a du CO2 et du calcaire.
C'est tout.
C'est les deux.
pour l'équipe. Merci.
Bonjour, docteur. Merci pour la présentation. J'aimerais savoir, est-ce que... Bon, comme j'ai eu... C'est la même chose. Vous allez me dire. Donc, j'aimerais savoir, le saumure que vous renvoyez dans l'eau de mer, est-ce que vous avez songé à son recyclage pour faire d'autres choses? Pour l'utiliser au lieu de le renvoyer dans la mer.
Bon, il y avait une possibilité de l'utiliser, de mettre des marins, des salins, pour l'utiliser en sel, mais on ne peut pas le consommer en fait. En Occident, en Europe, on l'utilise pour des déchets où on n'a pas ces besoins-là. Donc, il n'y a pas beaucoup de valeur ajoutée si on veut le faire. On veut valoriser ça ici au Sénégal. Donc, c'est pour cela qu'on rejette directement à la mer.
Alors, before leaving, please, Ousmane, une petite question. Est-ce que le projet-là verra le jour? Will this project be really seen? Because a few months ago, we have heard that the project was cancelled. And it seems now that it is reopened.
Mes félicitations. Hein. Je pense que c'est un projet futuriste pour l'Afrique. C'est des choses qui se font aisément en Europe où ils ont des problèmes d'eau potable. Moi, je suis ivoirien, mais en tant que tel, je suis surpris qu'un problème d'eau potable se pose au Sénégal jusqu'à ce que vous pensiez à dessaliner l'eau de mer. Je suis surpris. Il y a suffisamment d'eau douce au Sénégal. Est-ce que cette usine-là n'est pas exagérément cher pour le Sénégal? On peut même prendre de l'eau à l'intérieur du pays, l'acheminer à Dakar. Pour moi, ça serait moins cher que de faire des usines de dessalement qui coûtent cher en construction et en entretien. Parce que l'eau de mer, il faut constamment contrôler. Il n'y a pas que les eaux, il y a d'autres types de pollution. Ça me semble un projet futuriste, mais pour moi, ce n'est pas utile pour le Sénégal actuellement. Est-ce que j'ai tort?
Absolument.
Il a tort.
Tous les forages qui alimentent Dakar sont presque menacés par l'intrusion saline. Parce que tellement que c'est exploité de manière minière, ça veut dire qu'on ne l'exploite pas au début de renouvellement, de régénération des forages. Mais on l'exploite au-delà de ce début-là. Donc nous sommes en train de dégrader l'ensemble de nos forages. Donc l'usine, ça vient non seulement pour diversifier, pour réduire notre dépendance par rapport au lac de Guerre, aussi pour sauvegarder les forages que nous sommes en train d'exploiter. Donc avec cette usine, on va arrêter les forages qu'on a créés à Dakar pour les laisser se régénérer. Et parce qu'il y a l'eau de mer qui est en train d'entrer à Dakar. Parce que si vous voyez au niveau de Dakar jusqu'à l'aéroport
tous les forages que vous allez là-bas, vous allez des forages qui sont très salines, qui deviennent saumâtres. Parce que pourquoi? Parce qu'on les a tellement exploités que, parce que vous voyez, l'eau de mer et la nappe sont en équilibre en fait. Étant donné que la nappe a plus de pression, la nappe repousse l'eau de mer. Mais plus que nous, on exploite, il y a une dépression que nous sommes en train de faire. Donc, et la mer entre en continent et ça devient de plus en plus problématique pour nos forages. Donc, ça peut être un luxe, c'est cher, on comprend, mais de manière environnementale, ça nous permet, nous, de sauvegarder et de réduire économiquement, c'est une stratégie de sécurité nationale, de réduire notre dépendance par rapport au lac de Guerre qui se trouve à 250 km. Et on a vécu le problème en 2013 lorsque la conduite, on a eu un problème sur la conduite, on est resté 40% des Dakarois sont restés sans eau pendant 2 semaines. Et c'est problématique pour un État ne peut pas gérer ces pressions-là. On sait qu'on a assez d'eau, mais il faut mobiliser cette eau-là. Et ça demande beaucoup de moyens aussi.
Thank you, thank you, thank you. Hello. We have a technical talk, and I'm privileged to introduce to us Dr. Alejandra Palemo. I am privileged to introduce to us this Shiro, not hero, Shiro. Yes, she is a chemical engineer with a PhD in material science and a former researcher and an academic. She is responsible for global inclusion at RSC, leading a team that have galvanized most of us in Africa. She has been strategic in lots of things she does for inclusion and diversity in the chemical sciences. Currently, she is a fellow of Royal Society of Chemistry, a life fellow of the Chemical Research Society of India, and an honorary fellow of the Chemical Society of Ethiopia, and since 2023, she's a member of the Executive Board of Commonwealth Chemistry, and more recently, she has been selected as a member of the Science Board of IUPAC. I think she deserves an applause for that. She deserves a good applause for that. That is the highest making body of IUPAC, which all of us supposed to be members. And she's also a member of EU Chem Inclusion and Diversity Task Group since 2022. And now she's going to make a presentation to all of us on inclusion and diversity focused on gender parity and disability in the chemical sciences. Please welcome her to the stage. Thank you.
Thank you very much, Professor Obensur, for a fantastic introduction. Good morning, everyone. It's a great pleasure for me to be here today and talking to all of you about inclusion and diversity and our efforts to make the chemical sciences more inclusive. But before I do that, before I start with my presentation, my colleague and I, Professor Vincent Nyamori from Durban University in South Africa, KwaZulu-Natal University in South Africa, we have a video to share with you. So whenever you're ready.
I'm Martin Polyakov from the University of Nottingham.
That's for sure is not us here. I apologize on their behalf. So I just want to recap. I think most of us have heard of the green chemistry principles, which are highlighted here, 1 to 12, from prevention to less hazardous materials to safer ways of doing chemistry as your number 12 principle. It's something that Paul Anastas developed early in the 90s. But in this conference that was held in Ethiopia, Addis Ababa, which I happened to be part of it, there was Neil Colville, there was Johannes, and many of us that have been part of FAST for a while. We thought that it was an interesting topic that was given, an interesting talk that was given to us within the continent. We found it as a quite thought-provoking discussion, and I thought it was important for us to share what Martin thought is relevant to the continent. And if we look at to the discussions that took place, it was very clear from the outcome that Africa as a continent has got different experiences, different challenges. As much as we are all sort of put together in a common understanding of the Sustainable Development Goals, but the priorities and the challenges and the intensities are different from one region to another, even within the continent itself. But as African societies, we need to approach it in a different way. Hence, the 12 principles needed to be looked at in a different angle. And it was clear that the challenges needed to be tweaked. For example, in African continent, where we look at waste, we'll use as an example, mainly we look at waste, which is wet organic matter. But if you go to industrialized societies, advanced countries, most of their waste is slightly different. There is more of what, paper, metals, nuclear waste and stuff like that that we are not exposed to. So we need to address our issues and challenges in a slightly different way. If you look at those 13 principles that were laid out, one or two come out very strongly. One was the new ideas and different thinking, which again sort of rehashes what the IUPAC president was trying to say, that we need to think critically what is important to us as a continent. We need to be more innovative in what we've got. So we need to think about the indigenous knowledge that we've got in plenty, the indigenous renewable feedstock that we've got, and it highlights clearly that Africa is rich. But what is rich? Rich is what you need to do with what you've got. So we need to look at, for example, we have so much blessed with the sunshine, the sunlight. What do you do with that? Some other continents don't have that. We've got quite a wide range of renewable feedstock, which other people don't have. So we need to think about our skills, our technological advancements, to try and convert things, to drive our economy into more sustainable sort of society, so that we can have also an edge or move to ourselves where we're almost to where other countries are, to be part of the other nations, to be included, to be inclusive. That's why it's sort of relevant in this particular technical report. We need to be part of other developing nations. So, having said that, the last point that was addressed as principle number 13, which I found, we might look at it politically, but it's not political. We have seen other people experience challenges that we haven't yet experienced because we are not yet there. But we need to learn from other people, the other people's mistakes. And with that, we should be able to advance ourselves. So I will not speak much because time does not allow us. I'll allow my colleague Ali to continue with the other part.
Another big thank you for this presentation.
Well, thank you too. I don't know what that.
Thank you, Vincent. Thank you very much.
Very helpful. And so, you know, on one of the slides, what could work better, you had 2 points that I think are sort of related, and I want to ask your advice on. It's around fully applying the principles of country ownership and avoiding, you know, micromanagement. I think those two are very related, you know, it's MCC trying to be responsive to the policies and everything. But I think also it's, you know, at times, country leadership team members like us are actually probably some of your best advocates for country ownership and
Okay, now, I hope they can hear me now.
But it can be a difficult conversation because, you know, technical leads have a strong sense of responsibility and certain outcomes. So my request for guidance is around, you know, as we are working with our technical leads and micromanagement, how do those issues obstruct? Can you tie it to, you know, how do those issues obstruct results? So how would increased country ownership, reduced micromanagement, actually impact goals? Because I think if we can make that case better to our technical leads, then we have a stronger footing to arguments more often than not.
Okay, let's try again. So we were referring to a meeting that the Pan-Africa Chemistry Network organized in Addis Ababa in 2010, where we wrote this report, which is available on our website, about a greener Africa. And then after this meeting and the report that followed, Martin Polakov and a group of other scientists from Africa wrote an article in Green Chemistry Journal in 2011. The proposal is this is going to happen again. Martin Polakov, Vincent Nyamori, and other colleagues, Nigas Asfor from Ethiopia, and other scientists will write the updated version of this article. So I hope that you can follow that later on. So now to my presentation. I'm conscious about time, and I hope Professor Mamiya will help me to keep in time. So I'm going to talk about our work at the Royal Society of Chemistry in making, towards making the community, the chemical sciences community, more inclusive and diverse. First, I want to say a few words about the Royal Society of Chemistry for those of you who are not perhaps as familiar with the RSC. We are the oldest learned and professional body in the chemical sciences. We are a professional body and a membership body, and we have a very successful business, which is not for profit, and that means that all the benefit and all the commercial benefit that we have is back in the community. The photo that you can see here is a view of the Barnard House in London. So we at the Royal Society of Chemistry believe that chemistry should be for everyone, but unfortunately it isn't. So in order to help us move the dial a bit about inclusivity within the chemical sciences, we develop a strategy for inclusion and diversity.
Actually, the better.
Hello? Now it's better. Oh, sorry. Phew. So, our inclusion and diversity strategy, it has three main pillars. The first pillar is about taking an approach to inclusion and diversity that is based on data and evidence. We're all scientists, where we live in numbers. When numbers shows where we are, we can take actions and drive policies to drive change. The other main pillar is about providing opportunities for underrepresented groups to be attracted into chemistry and to fulfill their potential, that actually can progress to achieve what they want to achieve. And in particular, when we talk about underrepresented groups, who are those underrepresented groups in the chemical sciences? Well, there are many. Women in the senior positions, there are discrimination against disability, discrimination about sexual orientation, religion, race and ethnicity. There are many different people who actually are underrepresented in the chemical sciences, and towards them is where we want to actually drive difference, inclusive access and progression. But of course, chemistry is an international enterprise, and of course, we want to drive change across the chemical sciences, across the world. And that means working together. So empowering and influencing and working with partners is essential for actually achieving our strategy. Let me tell you a little bit about how it started, and this is a graph about what happens in the UK. In 2018, we embarked in a piece of research to look into the diversity landscape in the chemical sciences, in the UK and elsewhere. The data that shows here focuses on gender. And when we look at what happens in the UK, we see that despite the fact that we have an undergraduate distribution between male and female, more or less 50-50%, at senior positions we have a loss of talent, with only around 10% women in senior positions in the UK. And this is, as I said, this is the data that we can host in the UK, but we know there are different actions here, different countries that have different levels, ratios of undergraduates, male and female, but what we do know is the majority of individuals in senior positions in academia are men, wherever is the level of undergraduates starting point. And this is quite indicates a loss of talent as we go in the academic ladder. A similar proportion we see in industry. And this loss of talent requires a better understanding why is this happening. And so for this, in 2018, we look into the evidence behind the hard data, the numbers that we have presented. And we identified three main barriers. How we did with this? We actually produced a survey, we have focus groups, we interview many individuals in the UK and across the world, and we identified these three barriers. The first one is about academic funding structures that create uncertainty and unnecessary pressure in the community. And perhaps it's related to the common short-term funding models, short-term contracts. They are very common within the chemical sciences community. And also the pressure that we have to excel within the academic environment with the definition of what actually excellence is today. And reviewing what actually excellence means might be important. The other important barrier is academic culture that can drive individuals, talented chemists, elsewhere. And in particular, we talk about the inconsistent in leadership and in management in the environment, in the academic environment. We talk about the lack of sponsorship, the lack of effective networks for women.
The lack of a fair assignment of activities or responsibilities within academia. The other important barrier was about balancing responsibilities, which are different at different stages of your career. And the individuals that actually have responsibilities of care and responsibilities for family or children or elderly people. And that's, of course, any one of those barriers affect women and men, but they more disproportionately affect women. So one of the unexpected findings when we did this analysis, this piece of research, was the impact of bullying and harassment within the academia. And so we launched a support line, which anyone can actually access for free, to discuss the issues that you may suffer in academia or in the chemical sciences, wherever you're working. More importantly as well, we produced a video, which you can access here on YouTube, which actually describes what actually means bullying and harassment, and what you can do as an observer, and what are the actions that you can do. So I encourage you to have a look at this, either to use support line or the video. Knowing that to succeed in academia is important, the number of publications you have, because it's one of the measures of excellence today. We look at whether publishing in the chemical sciences is gender biased. So this is a piece of research that we had, and this is a report that we produced 4 years ago. And in this report, we look at all our journals over a period of 5 years, and we assign gender to names through a very common and very well-used methodology process. And with this analysis, we identify that there are issues that actually differentiate between women and men. One of those is that particular women are less likely to submit their work to higher impact factor journals. And of course, that has consequences. We also know that women in general terms tend to publish fewer papers than men. That compared to the total number of women that publish papers, there are fewer female researchers and who are reviewers. And we also know that papers written by women are cited much less than papers written by men. Citations are not only by men, but also by women. So women do not cite women, and men do not cite women. So with this report, we then develop a framework, and we produce a framework for action in scientific publishing, where how we encourage publishing bodies to actually make some difference and changes in their structures to improve gender parity. And after this framework, which is available on our website, this report, we also brought together publishers across STEM subjects and the social sciences to look together at how can we make a difference to make publishing much more inclusive and diverse. And particularly focusing on gender and race and ethnicity. But we hope that in the future covers all underrepresented groups in the chemical sciences and in the research community. And I wanted to mention this point because I think this is, we just started with this joint commitment across publishers across the world. We have commercial publishers and all non-commercial publishers signing up to this framework for action. I think we are seeing the tip of the iceberg. Hopefully, there will be a significant change in the years to come in terms of the research community and the inclusivity aspect. The other area that I wanted to talk in particular is about disability. And I will briefly describe what actually means with disability. In 2022, we have the RSC's membership survey. So many of you who are members will receive an action to actually respond to a survey. And this pie chart here represents the disabilities that individuals, members, declare. And as we can see in the chemical sciences community, the three main areas or four main areas of disabilities are long-term health conditions, mental health conditions, mobility impairment, and there's another part which is actually, I prefer not to say what my disability is. So we recognize that actually disability is an umbrella term that encompasses many different areas that actually affect the well-being and the day-to-day work of the individuals. So the first thing we did is to look at how we define disability and what way we can define in an inclusive way the term disability. So we adopted the social model of disability, which actually means that an individual is not disabled by themselves, but instead by the societal construction, the environment where they live. Which means that an individual feels disabled because it has inaccessible environments or because it suffers discrimination. And this model, the social model of disability, is important because it's an inclusive model, as I said, and it actually challenges the current views of disability. First, about the medical model, which actually this person is ill, we need to change their environment. And the other model, which is the charity model, which actually feels sorry for the individual who is disabled. So what we are saying here is that we insist that society must change. It's not that the disabled chemist needs to change. And it has very important implications, this. I can't go in more detail. So further in our survey, we asked in the survey questions, the first question is, do you self-identify as a disabled person? So only 4% of the members responding to this question declare disabilities, declare self-disabled, themselves are disabled. When we ask the same question, do you experience barriers or limitations in your day-to-day job? Around 10% of our members said yes, but they don't consider disabled. And the question is about why these barriers to self-identification as disabled. There are many, and I just want to mention just a few. One of those is the stigma associated with being disabled. Being afraid of having further discrimination as if they declare they're disabled. The lack of diagnosis, people suffer day-to-day impairments in their job, but they haven't been diagnosed. So this is a medical issue. And the lack of perhaps imposter syndrome. I'm not disabled enough to declare, but I do have an impairment. So there are lots of issues around the disability that are important to understand. So what has the RSC done so far and what we are doing so far? Well, there are lots of things that we have done, but in particular, we created a community. We got much closer to the disabled chemistry community and understand the issues, understand where and how we can help. So there is a new disability web hub in our website, and I will encourage you to have a look at it. There is much more information than I just mentioned in a few minutes. There are accessibility grants if you are disabled and you need support to attend a meeting or a professional activity that will help you in your progress. There are grants that you can have access up to £1,200 a year to support you. There are many different webinars and that we have offered to progress in your career, to help you to produce your CVs and so forth. And so many different things that we have done in the last few years, and this is the beginning of what we're doing in disability. More important is we are creating that community of disabled chemists who are more easy to talk and open about their issues. The last point that I want to take about disability is we just launched a new piece of research, which is about accessibility to labs. And we know, of course, majority of chemists use labs in a day-to-day job, or to study as an undergraduate. We know that not all chemical labs are inclusive for disabled chemists. So we are trying to understand the issues behind this. We are producing a survey, so you probably heard about this. And we are going to focus groups and better understanding. So with the aim of having a report about how accessible are the labs in the chemical sciences across the world, and what can you do, what are small changes you can do in your lab to make a difference to disabled chemists, or what small or bigger differences. And we learned quite a lot from countries all around the world of small changes that make a huge difference to individuals. So look out for that report early in the summer, 2025. I think I wanted to finalize with a sense of belonging. This is a report that we launched a few years ago, which talks about the feeling of belonging of individuals in the chemical sciences, how important it is for every chemist to feel they belong to chemistry. And the feeling of belonging is not a constant feeling, it comes ups and down, it moves ups and down. So there is quite a lot in this report, which is very interesting for you to read, perhaps. And we are committed to actually tackling the issues of inequalities in the chemical sciences. And we know that unless people feel they belong, they are very unlikely to thrive in their profession. We know that belonging matters, and belong is not only about the well-being, it will ensure that we have better science. So finally, I would say that what we believe is every scientist should be able to reach their full potential. All of us should be able to feel that we can reach our full potential. And that's what we are working towards with you, with many other organizations and many other communities across the world. This is a list of resources, and there are plenty on the website, and with this I stop, and I'm happy to answer any questions if we have time. Thank you very much for your attention.
Thank you very much for your presentation. Any comments? I believe the points are well taken, that all should have inclusion and diversity wherever that we are working in the chemical sciences. Thank you, Madam.
Okay. You are ready? Thank you very much. My name is Bejembo, Associate Professor in University of Anta Diop. It's a great honor for me to participate in the Pan-African Chemistry Congress, particularly to preside one of the science. I'm going to introduce Professor Alpha Ousmane Touré, who will present us his plenary conference, which focuses on title. The title, please. Industrial decarbonization deal with the net zero. Industrial was to decarbonize the cement and concrete industry. Before the presentation, allow me to read some lines about the bibliography of Alpha Ousmane Touré. Professor Alpha Ousmane Touré is an associate professor of Processes Engineering at Cheikh Anta Diop University of Dakar. He is a coordinator of the undergraduate program of Chemical Engineering at École Supérieure Polytechnique. Prof. Touré has over 12 years in industrial waste valorization as a Fulbright School who has served on the research faculty at Oregon State University from 28 to 29. Prof. Touré has international exchange experience for a joint research project with Howard University at Washington, D.C., Oregon State University, the City University of New York, and the National Polytechnic Institute of Toulouse. He coordinates the collaborative online international learning program with Lehman College at the City University of New York, etc. Prof. Alpha Ousmane Touré, you go it.
Okay, thank you, dear colleague, Professor Mbo. Good morning, everyone. I was supposed to leave before 1 p.m. since I have to take back my children at home, but I will try to handle it. Okay, 8 years ago, I was giving a presentation. On recycling waste from fiberglass during CSC annual days right here in Dakar. And today, I'm going to talk about industrial decarbonization deal with a net zero under the acronym ID 2.0, and particularly on industrial waste to decarbonize the cement and concrete industries. So let me welcome the non-Senegalese participant to our beautiful country with so many natural resources that we need to transform by ourselves. We have a big amount of natural resources, and from these natural resources, we generate a big quantity of waste materials. And as an engineer in chemical engineering, I have been working on industrial waste when I was graduating in 2004 at ESP, at the Chemical Engineering and Applied Biology Department. At this department, we are 25 faculty members and 580 students. Our majors in academic programs are chemical engineering, biology, food engineering, biotechnology, quality, hygiene, safety, and environment. And we are opening a new academic program on bioenergies and green technologies. Like I said, I have a passion on working on urban and industrial waste valorization, water and wastewater treatment, low carbon cement, integration of renewables into chemical processing, hydrogen, and right now in industrial decarbonization. So you can find out more on my research activities when you go to my personal website, right here. Okay, so. I have an issue with the pointer. Pointer, they have a clicker. Okay, now. Okay, I'm not yet. I was focused on recycling industrial waste materials in order to minimize damage to the environment in the production of cement and concrete, and also trying to recycle industrial waste products to avoid dumping them into the ocean or heap storage or atmospheric pollution. Because we are facing an ecological and social transition. This ecological and social transition was predicted by the one that I consider as the greatest ever scientist in Africa, Cheikh Anta Diop. Let's take a look at these statements when he was giving a talk in Kinshasa just 1 year before he died. So this is what we are facing right now, and this was said how many years? That's what we are working right now. We are working on decarbonization, working on hydrogen, and trying to build sustainable chemistry. For this talk, I'm going to divide it into four parts in terms of questions and according to this outline. So why we need to decarbonize the heavy industries? As you know, we have here 5 hard-to-abate sectors, meaning that for these sectors, it is very difficult to cut their CO2 emissions. We have also emissions from burning fossil fuels, and this is going to rise over years. Since we have here up to 0.8% compared with 2023. Now, when it comes to the cement, it's not about only burning fossil fuels, but we have here a combustion. When we try to use limestone, so burning limestone to obtain clinker generates big amount of CO2, and it is up to 60%. So 60% CO2 emissions are from the calcination process and not only about burning fossil fuels. And cement manufacturing consumes a big quantity of energy. And we can see here that for the cement, it is about 8% of global CO2 emissions. And cement is the key ingredient for concrete. Concrete is made of cement, water, and aggregate. To make cement, we have to burn limestone and clay in order to obtain clinker. Clinker also is the main ingredient of cement. Right here, when you take a look at this slide, we can see that there is a roadmap for cement in order to reach carbon neutrality by 2060. So this will allow reducing energy consumption in construction materials, low temperatures processing, and carry out cheaper construction materials. But also circular economy. So when it comes to circular economy, I define it just as processing with zero waste materials. As we are also facing global warming, and there are some scenarios here. According to the Paris Agreement, we're talking about 1.5 degrees Celsius. But if we do not do anything, we will reach more than 1.5 over years. So this is also a global warning. So we have some solutions in order to help industries decarbonizing their process. We have process intensification, which is an approach to making significant improvement to manufacturing, which improves energy efficiency, sustainability, and cost effectiveness. So PI is of vital importance for reducing the impact of climate change from the industrial sector, and will help to reduce the long-term ecological and social impact. In order to do this, because there is an urgency to act quickly, we need to collaborate, we need to innovate, and also we need to digitalize. So universities must work with industries in order to help them do things differently by using new technology, and this will enable the change and also will help us struggling with climate change. The U.S. Department of Energy identified 4 key pillars in the near, mid, and long term for decarbonization. We have energy efficiency, we have electrification, we have low carbon fuel, feedstock, and energy sources, but also we have carbon capture, utilization, and storage. So this needs a rapid deployment and adoption of new carbon and non-carbon technology solutions. So maybe it's going to be very difficult for Africa because until now, there is no policy for global industrial decarbonization. How to decarbonize the CCI? We can use clean power, and by using clean power, it might be power to X or X to power. We can use also mineralization. This will allow operating at a lower temperature, and even we can reach negative carbon concrete, because concrete is a sink of CO2. So concrete can absorb CO2. We need to use also alternative feedstocks like supplementary cementitious materials, like geopolymer, and more importantly, decarbonated materials. Because in the process of producing cement, we release CO2. If we can replace some raw materials with decarbonated materials, that can help to capture the CO2 in order to form calcium carbonate. So new feedstocks are right now being developed in order to substitute clinker up to 50%. Cement industries are working on calcined clay in order to manufacture limestone calcined clay cement, known as CLC. But we also have another feedstock, which is calcium silicate. By the way, calcium silicate is the main ingredient for cement, and it is a decarbonate material. It seems a very promising feedstock. Over years, we was trying to recover a byproduct. I will show you some published papers, and we obtained a calcium silicate, which is a decarbonate material that we tested, and it is a very high performance material that can help decarbonizing the cement and concrete industries. So, like I said before, you can find out more on the papers that I published since 2015. Cement or low carbon cement is not only my research activities, but I have published several papers on this topic. Like here, just want to share some chemical reaction from the beneficiation of phosphoric acid, which is a byproduct for phosphoric acid production. We have also phosphogypsum. So when sulfuric acid attacks the phosphate rock, we have phosphoric acid, but we have also a mixture of stream of gases, and the combination of these gases can form fluosilicic acid. So this byproduct can be used to produce calcium silicate. And we carry out so many processes in order to work up these byproducts. Finally, we have here a mixture of calcium fluoride and calcium silicate. So this mixture is very important, like it is shown in this process flow diagram. We use this mixture in the raw mill for cement, and this helps decrease the temperature of clinkerization and also reduce the CO2 emissions. We also did the carbonation process using CO2, because when you use CO2 with calcium silicate, you can obtain calcium carbonate, and that can help recover the CO2 from industrial process. So our materials have very interesting chemical composition compared with the chemical composition of OPC, ordinary Portland cement, clinker. We have the raw materials here. It's not the raw material, but the byproducts that we use. And when we take a look here, okay, when we take a look at the main oxide, which are calcium oxide, silica, alumina, and ferrous oxide, we do not see a big difference from OPC clinker and the calcium silicate clinker. And that's why we were trying to use this in order to reduce the quantity of clinker for cement manufacturing. During our Fulbright program at Oregon State University, we met some unfired bricks, because according to me, it's not very important to operate at high temperature. In some countries like Africa, where energy is an issue. So I did all this at room temperature and atmospheric pressure. I'm not here to show data or results, but I just want to share with you the work that I did in order to manufacture some building materials. So we did some characterization in order to determine the properties of our materials, like the rate of water for the bricks that were unfired bricks. This is not very clear, but this slide shows the carbonation process that we carry out. We have a calcium silicate and that can absorb the CO2 emission. We have also a very high rate of carbonation compared to the carbonation of wollastonite, and these results will highlight here. The compression strength also, when we do the alkali activation of our CSH, also highlights very interesting results in terms of compressive strength. I have here a table just to give you an idea of the amount of products or raw materials worldwide in Africa and in Senegal. So PA is phosphoric acid. PG is also phosphogypsum. We have coal and coal fly ash. And at last we have OPC, which means ordinary Portland cement. So many formula was developed over years with phosphogypsum, coal fly ash, calcium silicate, and also with waste of glass powder. Meaning that we can replace up to 66% of limestone for clinker manufacturing. And this will allow reducing the CO2 emission up to 6%, and also energy consumption up to 46%. Like I said before, we trying to recycle, and that can help with cement industries to produce sustainable and environmentally friendly cement. Our aim is also to lower the temperature of clinker manufacturing, to reduce the CO2 emission in order to cope with energy and cost efficiency. And we also try to use alternative fuel. We'll go through this. To sum up, I can say that we find out that we can use solid gas or liquid waste in order to build sustainable architecture. So this is a question, and I do believe that we can recover all kinds of waste as building materials. We also use more than 6% of phosphogypsum because phosphogypsum is being used in cement manufacturing, but the amount is very low. We're trying to raise the bar here in order to produce or to recycle a big amount of phosphogypsum. We all know that coal fly ash is 100% recyclable in building materials. The fluoric acid that we use also was 100% recyclable by using wet process with zero CO2 emissions. We designed unfired bricks at room temperature and atmospheric pressure. And also we are right now working on materials for road, and mostly by using phosphogypsum. Waste of glass powder also was used in our research. We use also slum, some residue from phosphate extraction, and most importantly, the CO2 capture that we use for concrete. We are trying to use black furnace slag as cementitious materials, and we are working on a project here just to decarbonize the cement and concrete industry by using our calcium silicate materials. So this project is between Oregon State University and ESP. And a student of mine is right now at OSU for her PhD program, and hopefully we'll come up with very interesting results. So what's the next? So the next step is to work on alternative fuel by combining hydrogen, because hydrogen is supposed to be the solution of the future, like Sheikh Anta Diop said many years ago. Africa has a big potential of green hydrogen production. This is the highest amount compared to the other continents. So I will finish my talk by saying that as scientists and engineers, we should break down the need to know. We should raise awareness on the global challenges that matter most to the decision and policy makers to society in order to save our planet by integrity, by respect also. So this work was done with some students of mine, with a collaboration between these universities, and I would like to thank the U.S. Department of Energy for my Fulbright, and also the West African Research Association, and UCAT also for the sustainable development activities that we are working on. We need to go far and quickly, and there is a state of emergency. Thank you for your attention. If you have any questions.
Thank you very much, Professor Alpha Ousmane Touré, for your presentation, which is so clear and very important. So someone to ask question or contribution? Okay, it's good. Okay.
Good morning. My name is Professor Rokhaya Silage. I'm a pharmacist at the Faculty of Medicine, Pharmacy and Odontology of University Sheikh Anta Diop, and my specialty is inorganic chemistry. And we are going to introduce Dr. Andrew Shaw. Dr. Andrew Shaw has a PhD in geochemistry. He leads the Pan-African Chemistry Network, collaborates and engages with EUCHEMS and UPAC on behalf of the Royal Society of Chemistry, and leads the international engagement activities with their global network of partner chemical societies. He is also secretary to the Commonwealth Chemistry Executive Board and part of the Commonwealth Chemistry Secretariat. He has a demonstrated history of working in publishing industry. That's why we are going to talk about open access and open science in publishing.
Merci beaucoup, Madame. Good afternoon, everyone. My apologies that I'm keeping you from lunch, so I will try and move through, and I'm happy to take questions during lunch and to the rest of the day as well. So please don't worry if there's no questions straight away. So my colleague Ali, at the end of beginning of her talk, said that chemistry is for everyone, and really my talk really fits very nicely into that, because chemistry for everyone means you've got to have access to knowledge. And so to have access to knowledge, you've got to have open access and open science. And that really fits very nicely. And that's what I'm going to talk to you about today. So my talk, perfect, merci, is going to be in two parts on a bit of background to open access and open science, and also then particularly focusing on the approaches and the role and the way the RSC is approaching open access. So when we think of open science, the very top, let's see if I can. Yes. So we think of open access as being about knowledge and information, but actually open science is more than that. It's about having open infrastructure, it's having open resources, it's about actually engaging with each other and having open conversations and open discussions with all the people involved. That could be researchers, that might be funders, that might be the universities, that might be people like us as the RSC, publishers and societies. And it's also about having open engagement with other systems. So it's much wider than just knowledge. Open science is much more than that. And I'll talk about open access, which is probably the most important part of the open science conversation. At the RSC, we have a very strong commitment to open science. And it is about working, importantly, with our community to break down the barriers to ensure that the chemical sciences are equitable, that is global access to knowledge and to data. And you can see the full statement there, but it's about breaking down those barriers to advance our excellence, but in an equitable and a global way. When we talk about open science at the RSC, there are four main areas that we focus on, and I'll break those down. So we talk about open research data. So all of your publications have a multitude and a huge amount of data that's associated with them. But that data is often just lost in a database, or it's on your computer, or it might be in electronic information that is a PDF. Well, that's no use to anybody. So at the RSC, we want data to be made available. That could be through the publication itself, or depositing that data in your university repositories or your institutions, and linking to it, whichever way you want to do it. It's up to you, and it's up to what your funder wants to do as well. But it's about making data findable, accessible, usable across multiple platforms, and reusable. So the acronym FAIR is used there. The peer review process that you all go through when you're publishing your papers is quite closed at the moment. We want that to be more open. So currently, all the RSC journals are transferring to what we call sort of a transparent peer review process, where the reviewers' reports are still anonymous, very importantly, but they're available for people to read alongside the published paper, as well as the decision letter of that editor. So you start to understand the process that paper has gone through, from it being submitted to it being published. And all journals are starting to offer that option. Chemical Science, our flagship journal, also offers authors to choose what we call double anonymized peer review. So currently, the reviewers are anonymous, but the authors are known to the reviewer. A double anonymized peer review is where both the author and the reviewers are anonymized to each other. So it potentially reduces bias in the peer review process. There's also a wider piece about research assessment and research culture. The RSC, along with many organizations, publishing organizations, sign up to DORA, the Declaration on Research Assessment. And this is really a commitment to improving how research is evaluated. We all know about impact factors. The impact factor is one number among so many amazing other metrics that are out there, and we believe in making the impact factor just one of many other factors that can be improved, and in helping to support our community in making research and scholarly research and a better evaluation. And then we come into open access, and I'll come on to more of that detail later on in my talk. So, I talked about open science being much broader than just the actual papers itself. But yes, open access here is one of the key aspects of scientific knowledge, along with data, resources, open software, open hardware. Why am I talking about open access? Why is it a conversation that probably you might be having in your departments, with your colleagues, internationally, nationally? It is effectively the future. It's not when, it's not sort of if, sorry, it's when, really, with open access. There are real benefits. Speed. It's fair. Everyone can read a paper. It's visibility. All papers have greater visibility if they're open access. There are a number of studies that say there's increased downloads, increased usage, increased citations. It helps much more of an interdisciplinary collaborations. It allows this world we live in to become much smaller, actually, and allow people to really work on problems with each other. And it also allows for much more transparency in research. And we believe, and along with many other publishers, that open access is the best and most efficient way to help chemists exchange knowledge. As I said, it is the future. It's no longer if, it's when, but importantly, how. How will open access happen? And that's really the conversation we want to have. The current open access model of article processing charges and paying things like that, authors paying for publication, isn't necessarily, it's not sustainable. There has to be alternative models. We've got to look at ways, but it's got to be ways that work for everyone. And what I say in Europe is going to be very different to what might be different in Africa or in Asia or in North America. And that's really the key. We want to understand from our communities what open access means for you and how best to make open access work. Some examples. In Europe, all research funded by most of the European agencies has to be published open access. The US, in quite a significant change actually, will require immediate access to all of their federally, so government-funded research starting in 2026. Japan have also announced a change in 2025. Australia are looking at national open access deals. But importantly, librarians around the world and publishers are trying to adapt and amend and change things and transition so that this can happen in an equitable and fair way. When we talk about open access, most people think of green and gold are the two sort of primary routes. So a green open access route is usually without a charge, but there is a delay in when that paper can be published in a repository. Or there's gold, which is where there is then a charge involved, which can then happen as soon as that, the paper is ready to be published. But I wanted just to point out another area which is a form of open access, and that is preprints. So within chemistry, we have ChemArchive, which is a preprint server. Those of you perhaps on the more physical side might know of arXiv. There's also bioRxiv, so all the STEM subjects are represented. But ChemArchive is an opportunity to put your submitted paper, so the paper you've submitted to a journal, into an archive. It receives a DOI, so therefore you can cite it, it's searchable, it can be found while the paper is being peer-reviewed, while it's going through the peer review process. And the advantages of preprints, it's fast. You can, I think, you know, that you can post it and it'll be online within 24 hours. It's archived, so it's permanent. You have a DOI. Importantly, in this world we live in, it establishes a precedent, so it allows you to say, this is my work, and I've done this work potentially earlier than it would be seen if it had gone through the peer review process. As I said, it can be submitted before you submit it to a journal or while it's under peer review. You can update that paper as you're going through the process. People can comment on that paper. In Archive, which is the more established one, often people will put a paper up and then wait, say, 5 or 6 months, gather comments from the community that strengthens their paper, and then submit it to a journal. So there's another opportunity there. And you can submit that preprint to a journal, and through ChemArchive, there's a quick way of submitting it to actually a number of journal houses, not just the RSC, the ACS, the Chemical Society of Japan. The RSC is just one of the publishers involved. So I wanted just to talk about preprints a little bit, as that might be something a bit new for people. Thinking about the RSC specifically and open access. So the RSC has been talking about open access for many, many years, more than 10 years. About 2012, we introduced a system where we sort of had gold for gold. It was an opportunity for some of our subscribers to get access to vouchers to start publishing their work open access. We've transitioned many journals, so Chemical Science became open access in 2015, RSC Advances became, which at the time was the world's largest chemistry journal, became open access in 2017. Since then, we have really made a big effort to increase the volume of our journals that are open access, both fully open access or sort of hybrid. And we have a commitment that we will be the first chemistry publisher, we were the first chemistry publisher to say this, to be fully open access by sort of 2028 or within sort of 5 years. This is just a selection of some of our open access journals. It may cover the whole breadth of chemistry amongst the within our fields, from environmental, from digital, materials, polymers, interfaces, chemical biology, pharmaceuticals, sustainability, sensors, batteries, solar, just a few there. And all of this information you can find on our website. I'm obviously speaking to a fantastic African audience, so I wanted to really talk through access to some of these journals. And this is probably, if you remember anything before lunch, it's remember this, because this is a really, really powerful opportunity for all of you. The RSC, along with most other publishers within STEM, allow almost all countries in Africa free access to our subscription journals through a program called Research for Life. And I've put the website there. If you look at that, researchforlife.org/access. Your university has to be subscribed to this program. And I looked, and I think Senegal has 75 universities currently subscribed, including UCAD down the road, as one example. So have a look, see if your university is subscribed. If it is, then you can access all of the RSC journals, particularly those papers behind a paywall, for free within almost all of Africa. And that's also extended to open access. Anyone within Africa, almost within all of Africa, and there's a reason I'm saying that, can publish open access for free in an RSC journal. And again, that is wider than just the RSC. So have a look at this website there. It's a really important sort of opportunity for everyone, and it's not well known. That's the other important thing here. So I've been saying a lot about all of Africa. Those eagle-eyed amongst you will spot a country at the very south of Africa, South Africa, which unfortunately isn't included in this. And there is, but at the RSC, we're conscious of that. And so with the RSC, while there's not an automatic waiver, we have agreed it's a fantastic deal with a certain consortia in South Africa, and the number of universities there, which I think include most. So actually authors in those countries can publish and read our papers in those universities as well. But yes, I'll put the map back up just for people. As you can see, with the exception of South Africa, all countries within Africa, if they're either blue or orange, don't worry about the difference there, can access all of our journals and publish open access for free through Research for Life. And on the open access side, we do it through an email address. So we will look and see you're from an institute in Senegal, or Mali, or Mauritania, or Kenya, or Nigeria. And if you want to publish open access, you'll be given that option to do so. The last couple of slides now for me. As I said, we are really committed to open access as an organisation, and we are hoping, we announced just over 2 years ago, actually, 31st of October 2022, we announced a commitment to become 100% open access within sort of 5 years, so around 2028. We want to do this because it's about removing barriers. It comes back to that first point my colleague Ali said, chemistry is for everyone. We want all authors to have the same equal potential to access and publish research. Now, there's barriers in the way to do that, in terms of financial barriers, but the way we want to do this is moving away from models where you, our authors, have to pay, and to cover those fees with the institutions, with the funders. And so effectively it's transitioning from the same money that someone might have spent to pay for a journal that's in a traditional journal, subscription journal, that same money would be used to pay for open access charges. So it's not about getting more money, it's about just changing that money into something that supports open access rather than a paywalled article. But to do that, we need to talk to people. This is an example of this, me here, but we run a number of events across the world. We were in Kenya 3 weeks ago, we had a fantastic open access panel with some amazing people there, talking about how it can really work for Kenya and Africa. But we need to discuss with our communities how best to make open access work. So it's talking with the community, developing models that are going to work for individuals. I've talked about Research for Life, but that might not be necessarily the only one that's possible. And talking with people, researchers, librarians, about how to engage and deploy those models. As I said, we are the first chemistry publisher to commit to 100% open access, and we want to have these conversations with you. So talking with our Chemical Society partners through FASC, through Commonwealth Chemistry, through all of those sort of various federations, we have, talking and understanding and really supporting and finding a way that everyone can move with us to this really open future. So do come and talk to me, do come and look at our website, and do find out more about what we're trying to do. So I'm happy to take questions now or after lunch, but thank you very much for your attention.
There is some questions, yes?
So thank you. So the first question was on preprints, and it was if you put your paper on a preprint and then it's rejected, that paper is effectively there, and what can someone do? Could they take the data? Could they take the ideas? Effectively, by putting something on a preprint server, as I said, you are giving it, it's archived, it's searchable, and it has that digital identifier. So it becomes something that can be cited and also, therefore, can be found. So it becomes yours. It's acknowledged to you. So in that sense, if you have suspicion that someone has done that, then we can take any actions that need to happen if data has been stolen. But by putting it into a preprint, you've secured that it's yours, it's under your name, and the timestamp effectively is there. So yes, there is a risk to that, but at the same time, by putting it on a preprint, you've actually got a guarantee of that you were first, if that's sort of the situation. And then a publisher would take any action that was appropriate on an article, perhaps, that had been submitted or published using data that they shouldn't have used. So there is that confidence in that sense that you have that precedence. And as I said, if your paper is rejected, but then you revise it, you can then put a revised version on that preprint while it's still then that revised version is under submission too. So you can update that preprint with revised versions if you've made changes to help get that paper accepted. But it's a good point, but the idea of having it gives us more proof and understanding that that is your work. And that's why it's archived, why you've got those, why it can be searched. And people can cite preprints. Like you do a full article, you can put that DOI, so if you have a preprint that perhaps you don't want to publish, but the data is of interest, you can cite that paper and get that credit and link it to people, so it is citable. Yeah. Second question was about whether open access creates inequality, and then fundamentally, I think it can, but I think that's where our approach is to take away that barrier through finances, potentially from that individual, to move it towards institutions and or funders. So as I said, currently you might spend your library might pay to access an RSC journal, for example. We want, and under open access, currently, normally that cost comes to you as an individual. We are saying to librarians, if we are 100% open access, then the money that you would have spent to access those journals that aren't open access is now being used to support open access payment and charges. So it's changing the existing pool of money, potentially, and the use of that money. But I think, as I said, the other thing to go back to is the Research for Life scheme. And so currently, you're also in Tunisia, you would be able to publish for free open access through that Research for Life scheme. So that is our ambition, to try and remove some of those barriers currently, which obviously hits Africa and other parts of the global south predominantly. Thank you.
Any questions? Thank you, everybody.
Thank you. Merci.
Good afternoon, ladies and gentlemen. It gives me great pleasure to introduce our next plenary speaker, Professor Neil Koval, who comes from Johannesburg in South Africa. After obtaining his undergraduate degrees, he moved to McGill University in Canada, where he obtained his PhD. He then postdoced at Harvard University in Boston in the USA before returning home to Wits University, where he rose up the ranks from lecturer to full professor and now as an emeritus professor. He studied for a long time Fischer-Tropsch reactions because they were of great interest to South Africa's economy, and they entailed organometallic compounds, which he was an expert on. More recently, he has moved to carbon nanomaterials, which his talk is focused on today. Professor Koval has been the president of the South African Chemical Institute, the president of FASC, and he is currently the president of Commonwealth Chemistry. One thing about Professor Koval, he does not shy away from work. He is an extremely hard-working person. I know no other like him. Let's welcome Professor Koval.
Thank you, Vice. Right, so I'm the last person to talk this before lunch, so I'm going to get into my talk and tell you about some work we've been doing. The title has changed slightly from what I gave initially, and that's normal because I gave the title many months ago and things have moved on since then. And the work I'm going to talk about today relates to some work we've just published, basically. And so it's going to be different from many of the talks you've heard today, which have been focused on data. I want to talk to you about an idea that came about from working with a graduate student, and it shows you the type of information you can get if you start looking at data in more detail. So what I'm going to talk about is carbon and a novel use of hollow carbon spheres. And I'll tell you all about those as the time goes along. As mentioned, I'm at the University of Witwatersrand, is in Johannesburg. We call it WITS just because it's such a long name. Right, so let me get going. Right, so I come from Johannesburg, big city, and I'm now in Dakar, long way away. And Johannesburg is sort of in the center there, that blue dot, and it's a big city, and it's got a skyline, and it's been wonderful for me to come here and experience the culture and the languages and the food and the partying last night. So it's a great pleasure for me to be here, and I thank the organizers for setting up this conference and inviting all of us here. Right, so let's start at the beginning. So basically, if you look at nanotechnology, and that's what I'm going to talk about, is carbon in nanotechnology. And if you think about going back to the early beginnings, the real start starts with Richard Feynman, who made a statement many years ago, 1959, why cannot we write the entire 24 volumes of the Encyclopedia Britannica on a head of a pin? Nowadays, we don't think twice about that. We've got our smartphones and our computers that do more than that. But when this was proposed, it was amazing. And it goes back to the talk that was given by the president of IUPAC, how we can't predict the future, and nobody would have predicted what Feynman was saying as we stand here today. Not possible. But the element I want to talk about is carbon. Carbon itself has been at the forefront of this generation of nanotechnology. There were so if you look at it in terms of what's carbon good for, it's a lightweight element, so it's replaced many of the items that we had that were heavier. For example, think of carbon fibers, bicycles and so on, cars that are replacing iron with carbon. It's got a varying bonding capability, and this is why carbon is so important. It has that ability to form sp2, sp3 bonds, and it can even form, if you think about it in terms of when you start looking at molecular orbital theory, it can bind to 6 metal atoms in an octahedron where carbon's at the center of, say, 6 rhodium atoms. It's quite phenomenal in that way. It's abundant, so there's lots of it. We can all work with it. There's plenty of it. Of course, the most important point is associated with life processes, and many people have spent their lives, careers, spending time on this in looking at the medicinal components, the organic chemistry side of carbon. But I want to talk about nano and carbon that's inorganic, if you like. I'm not going to talk about where carbon's going with carbon superstructures. A colleague of mine, Somnath Bhattacharya, has just written this book on carbon superstructures, and it has to do with carbon in making quantum computers. But that's not what I'm going to talk about. So, when we think of carbon hybridization, as I say, we think of sp, sp2, sp3, and it's all to do with 2 electron bonds. But as you may have seen or not seen, there's an article that's just come out showing the direct evidence of crystal structure with a carbon-carbon 1 electron bond. It's been made because of the thinking of how you can do that, and you force 2 carbon atoms together so that they can move apart, but the proximity allows you to get 1 or 2 electrons in. And so there's a lot of carbon chemistry that can still be done today. Simple element. And as I say, it was published, you can't quite see it, but it was published a couple of months ago, this article. So when we think of carbon, in particular with carbon nanotechnology developments, it partly relates to carbon nanotubes, and Ijima was the one who popularized these types of materials because he saw the link between fullerene and the tip of a carbon nanotube. So all the chemistry you could do on a fullerene, you started thinking, aha, can I do it on a carbon nanotube? And that led to that direction. So Ijima didn't discover carbon nanotubes. They'd been known for 20, 30 years before that. But he was the one who linked and allowed that process to go forwards. So we got carbon nanotubes and module carbon nanotubes. But I don't want to talk about carbon nanotubes. I want to talk about carbons with spherical shapes. That's what's kept us busy for the last 10 or 15 years, these carbons. And there are various types. I've mentioned fullerenes, which are single-shelled carbon materials. You've got the carbon black, which is basically soot. You've got the hollow carbon spheres I'm going to talk about, and then you've got the most recent ones, onion-like carbon, nanocarbons, carbon dots, etc. I could have spoken about those as well, because we work with carbon spheres ourselves. But I want to concentrate on the hollow carbon sphere. We wrote a review on this, on carbon spheres some years ago. But if you look in the, on my right-hand side, you'll see at the bottom are three spheres, if you like. And a hollow carbon sphere is like a balloon. It's empty, but it's got a shell. So you get the solid carbon, the proper carbon itself, and you can put things inside, as I show you with that ball inside the middle of those three pictures. And when we think about hollow carbon spheres, we can do all sorts of things with them. And this has led us to do a lot of work over the last 10, 15 years, just working on hollow carbon spheres. So you can look at the size, you can change their size, you can change the width of the shell. And what's driven our direction, though, is I'm in the area of catalysis. And there was some work that came out with carbon nanotubes where they were putting metals, those green little balls, inside or outside of carbon nanotube, and they had different reactivity. So we started thinking, well, if we do the same, can we do the same with a carbon, hollow carbon sphere? Oh, thank you. That one. Oh, yes, thanks. So what we started looking at, because I work in catalysis, is given this, these are more difficult to work with, these are very simple to make. Could we then start looking at the difference when you put metals inside or outside of the carbon sphere? And that's work we've been working on for a while. And it leads you into industrial chemistry, as Biche mentioned. So how do we actually make the hollow carbon sphere? Because I've said we can get them, and it's actually very simple. These hollow carbon spheres you can make using templates. So a template is just, imagine you've got a ball, you cover it with something, and you remove the inside. And you can do that quite easily with chemical means. So you can have inside that ball, this inside part, you can have a polymer, you can have silica, anything that's removable and will leave the hollow carbon, leave the shell outside. There are a variety of methods for doing this, CVD methods, autoclave methods, and while I'm going to talk mainly about a catalytic process, these types of materials can be used for drug release, they're used in solar cells. We've used these, solar cells, sensors, catalyst supports, fuel cells, batteries, and so on. I'm not going to talk about the uses. I want to talk about a little idea of using these materials as we go along. And then, you know, looking at the HCSs, you can do so many things with them. You can dope them, you can functionalize them, you can vary the porosity, you can vary the thickness, the diameter, and these also have conductivity and strength issues. And here's an example of an electron microscopy picture showing these carbon spheres. So how do we make them? Very simple, as I mentioned. You have a template. So here's an example of ones we made. So you take a silica sphere. These are easy to make. They're stobospheres. Many of you may have made them yourselves. And what you do is you put the ruthenium, these little dots on the outside. It's easy to do. Cover with carbon layer. And we do this, for example, using toluene. You can take toluene, put it through an oven, and the toluene decomposes around this, and you get your material. And you, using sodium hydroxide or some base, you can actually remove that silica, and you land up with what you want, ruthenium particles inside the hollow carbon sphere. So, the issue that we faced when we started doing these, we were interested in the catalytic side, but the issue is, can we use the inside to do peculiar type chemistry, things that people hadn't done before, or because you've got a new material now to work with. And so the types of things we've been looking at was sintering, because you're limited by the amount of material inside the inside that sphere, so you can look at sintering effects, different size particles that you're controlling, and you can look at this by electron microscopy. We can grow structures. I'll give you one example of this. And what I want to talk about today, though, is something that many of you won't know about, that has to do with hydrogen storage and reducibility of metals, called the spillover effect. So again, we're looking at hollow carbon spheres, and here they are. They're just beautiful structures. So, what one's got to keep in mind with, you draw these cartoon pictures, and you've always got to remember what the actual shell looks like. These shells are porous, and they've got functional groups on side. This is what it really looks like. You've got carbon here. This is another sort of picture of it, if you like. Lots of aromatic rings, but lots of defects. So it's a very defective structure. And it allows for things to go inside and outside. So it's porous, and so you can move molecules, gases inside and outside. That's what drove us in this direction. And again, it was mentioned by our IUPAC president, how if you've got pentagons, you can get this a structure to give the spherical structure a shape. So, just to give you an example of some peculiar chemistry that's possible, this is work we did a couple of years back. I had a postdoc with me, and what we try to do is grow carbon in a copper hollow carbon sphere with acetylene. What were we trying to do? If you take copper and you pass acetylene over it, you can grow spirals, like springs. And but the thing is, you get a real mix. And we thought to ourselves, what if we could put the copper inside, the little particles, and then pass the acetylene over and grow carbon spheres, carbon fibers inside the structure. And you can see them possibly growing here. But more importantly, if you look here, here's our carbon sphere. We can grow things inside the carbon sphere. So here's your copper catalyst, and although it doesn't show too well, it's a spiral structure. And we're controlling now the type of spiral we're getting, because by doing it this way, we can change the copper size and look at the different spirals that are formed, which is what we did. You can show the inside by, for example, doing tilting experiments, and yeah, you can see it moves around as you tilt the microscope. But what I want to talk about today is what I find a more fascinating topic in some ways, is this spillover effect, work done by a PhD student, September Leffy. And spillover effects are used for metal reduction and hydrogen storage. So what happens is, when you're working with catalysts, you're normally working with a metal, but you get the stuff out the ground as a metal oxide, possibly as a metal sulfide. And what you've got to do is you've got to reduce that metal oxide to the metal. You do this by hydrogen, using hydrogen. But what you also do is you can add what's called a promoter to enhance the reaction. So by adding the promoter, you aid that reducibility. So what happens then is, if we've got two metals, that's the one I want to reduce. I reduce my first metal, and then the hydrogen spills over to the second metal. That's what spillover is all about. So we've got this metal here on top of some type of support, and the hydrogen's moving from here to here. So when you start looking at this, there are two potential ways this can happen, called primary spillover and secondary spillover. In primary spillover, it's sort of obvious. The metal sits here. I've chosen ruthenium with cobalt oxide. Hydrogen comes down. It spills over because the two are in contact. And this goes from copper oxide to copper, and you generate water. And why do we look at this specific system? Because cobalt is the Fischer-Tropsch catalyst. It's the one that makes fuels in South Africa. Big process. And ruthenium is one of the promoters that they use for doing this. So that's why we were looking at this specific example, because it allows us to look at that specific issue of reduction of a metal by a promoter. You can also, and this is where the spillover effect really becomes more interesting, is you can get spillover at a distance. So the ruthenium, the hydrogen comes on here, spills over, reduces the carbon oxide, and you get water coming off. And this can be an oxide or a carbon source. So it's spillover at a distance. So instead of them touching, you've now got them at a distance. So, well, how can we study this effect? So what you can do is you can make hollow carbon spheres, you can vary porosity, carbon thickness, and so on. So the promoter itself, if you put it on the outside and you put your metal inside, you've got a way of separating to look at the secondary effect. So when you've got the promoter here, you're going to reduce it, and the hydrogen's got to spill over to the metal through this carbon shell. So this is what we did. I had a student who looked at this, Tumelo, and we used the hydrogen carbon spheres to study the spillover. It took us a couple of years to get all this data, because it's not, you've got to collect lots of data over this. And really what we're doing is separating the promoter and the metal using a carbon layer. Our first study was with ruthenium outside, cobalt inside. We've since looked at promotion with platinum, ruthenium osmate. It all works, and you get this promotion effect. Clearly, the hydrogen carbon sphere, the HCS, has porosity to allow the hydrogen to move through. And what we're comparing is hydrogen coming directly onto the metal versus via spillover. Now, when you start thinking about this, and this is where we were lucky with some of our thinking going forward, is what about the distance effect? We know that we've said there's a distance that it can go over. Can we study that distance? And that's really what I want to talk about now. How can we get that studied? So if you look at the literature, you can separate the two by putting it on metal oxides, and you just put some promoter in between, and you can separate them, and you can study the effect. And that's been done. There's some beautiful work I'll show you in the next slide. Looking at this one, I'll come back to it. And this is what we're doing. We're separating the two by means of that carbon layer, and we're going to vary the support distance. So the work that was done, really elegant work, a couple of years ago, 2017 now, where what they did is they were basically using lithography to place metals on supports, and then they placed the promoter further apart, and they studied the effect. And it was a really good study. But this is very sophisticated. So we wanted something much simpler, and this is what we did with our carbon spheres. If you vary the distance, we can do what they were doing by lithography, but by just making our carbon spheres with different widths. So what we did is we've got D1, which is narrow, D2, which is broader, and we're going to study the effect of that distance on the spillover to try and get a sense of how far it can move, the hydrogen. We've done many studies on this, and I only want to talk about one specific one, which is called temperature programmed reduction. Now, many of you may not be aware of this, some will be, that all you do is you put your sample in a tube like this, you pass hydrogen through, and you've got a TC detector, GC, that monitors the amount of hydrogen coming through. So if you use it to reduce your metal, you get a lower peak, and you can monitor the reaction. So what do the peaks look like? So it's important to understand what actually is happening. So if you take cobalt, which is the catalyst we use because it's a Fischer-Tropsch catalyst, it goes in two steps. There's a cobalt oxide to COO, and the COO goes to CO, and this is in a 3-to-1 ratio. 3 of those go here, so you've got 3 waters coming off, or 3 hydrogens to 1. If you look at the hydrogen coming through the GC, which is what we're plotting here, you're looking at hydrogen uptake, and they always plot the peaks as positive, even though the hydrogen's being absorbed, versus temperature. You increase the temperature at which you're passing the hydrogen over the metal, you get the first peak, which corresponds to this, and the second peak, which corresponds to that. And what's important is the actual peak position. So by looking at the peak position and the heights, you get a sense of what's happening in the reaction. So this is a straightforward example. So now we come to look at a specific case where I was showing you hypothetical things. This is what it really looks like. So what we've done is we've taken cobalt, and that at sign means inside. That's the general term used when you've got a core shell structure. You put cobalt at whatever's on the outside, in this case, a hollow carbon sphere. And what we've done is we've taken 3 different diameters, 16, 28, and 51 nanometers. And what you'll notice, although there are complications with the data because we've got methane coming off and so on, but that's not a detail here. What we've got are the 2 peaks here. And what we're plotting in this part of the diagram is the important part. If you look at that peak, which is the second peak, there they are there. I've taken just those positions, 340, 335, and so on. And it's pretty much a straight line. If you look at the other peak, you'll notice that as the width changes, so this peak shifts and becomes more difficult to, it becomes easier to reduce as you go along like this, or more difficult to reduce as you go along like this. Keep in mind what we're looking at is the cobalt inside the hollow carbon sphere, no promoter. So we did this study to get our background data when we put the promoter on, because we wanted to see whether there were going to be diffusional issues with, because as you vary the width, so there's more distance to travel by the hydrogen as it enters the hollow carbon sphere. So we needed this data to actually make decisions as to whether we're really seeing something. So in essence, what we're doing is taking that peak and just plotting them like this. Okay, so that's the essence of it. We're taking the maxima and showing how it varies without a promoter. So the question is, what happens when we add the promoter? I'm not going to show you the actual pictures just because they're similar, but I want to show you the data. And the data, if we take, for example, this one here, which is the high temperature peak, the second peak, remember they were almost the same. When we add the osmium, and this is osmium as a promoter, it doesn't matter what that promoter is. What you'll notice is that we start at a much lower temperature, and as we vary the width of the carbon, so it becomes more difficult to reduce, which is what you'd expect some way if the hydrogen's got to move through the system. Similarly, if we look at this other peak, and remember that moves slightly, here we can move upwards, showing that the 2 are moving together. We could also plot by putting the osmium and cobalt inside, both of them simultaneously, to get the 0 point, and we plotted that there. And you can see it's pretty good shapes here. So what does that mean? And this is really what it's all about, is that we can get the distance over which hydrogen can occur in the systems we've got, and we get a measure of it. So here we've got, if you imagine this going up and up, and that's keeping pretty much constant, we can get that point, which is about 55 nanometers, which tells us that hydrogen can move 55 nanometers across a surface in its ability to reduce that peak. If we take the other one, you can see here, this one is going to occur way out here. So that means the hydrogen can travel further. So we have an ability then to monitor reactions, the distance over which hydrogen can move. As you'd expect, this is a much easier process, so you'd expect the hydrogen to move easier. It's the first step. It's the easiest reduction. And this one's the more difficult, and it's stopping quicker. So out of just studying, as I say, distance effects, which we didn't expect to get this type of data, we've been able to measure distances over which hydrogen can occur. What that means is if you're thinking of hydrogen storage, you've got all that distance that you could actually store hydrogen, because remember the hydrogen's moving across the surface as it goes from the promoter to the metal. So once you've got this effect, because this is really my story I wanted to tell, we can determine the distance to spill over, it varies with the oxidation state. What about other issues? Change the metal, it's going to vary. Change the promoter, it's going to vary. If we dope with carbon, and these are studies we're doing at the moment and have done some, the nitrogen is very important when you've got carbon, and this allows for easier promotion. Does it allow for easier hydrogen transfer, porosity, and so on? So there are many variables once you start going down this pathway. So that's really the story I want to tell you, a simple one, showing you that you can get really industrial information from just a simple student doing some work, and all of a sudden you see an opening that you never thought would emerge. And it's the whole idea of you can't predict what's out there. So Hydrogen carbon spheres can be used as nanoreactors. I showed you that, just one example. If we'd had more time, I could have spent a lot of time talking about that, how you can build things inside a inside a carbon sphere, and I showed you just how we made a helix, and also to study the properties of carbon. I've got to acknowledge various people who did this. I thank the Senator Lee's Chemical Society for setting up this meeting and inviting us all, students who did the work. I belong to a group called CatMat. Collaborators, in particular, there are two collaborators I work with who are really taking over. I'm on my way out and they're on their way up, so we're transferring the information across. Monoko and Roy, and they've taken over. These are not my students. They're part of a group we have. There are about 10 of us who work together. We've got 60 postgrads in the group, so it's a big consortium. This is just a Christmas party we had. Of course, all the funders that have come through. And before I end, I had to advertise FASC, because seeing I've worked with it and part of FASC is here. FASC, as for those who were at the AGM yesterday, would appreciate that we've got the executive, we've got the fees and so on, but individual members can join. And we put out a newsletter, I put that one out, and for those who want to become individual members, they can, they'll get the newsletter and so on, and all you've got to do is just go to the email or the website to sign in, basically. With that, I thank you for your attention.
Thank you very much, Neil, for a most informative talk. It was absolutely fantastic. I think we are so late that I am not going to allow any questions. If you want to discuss matters with Neil, you can see him down at lunch. So thank you, everyone, for persevering in this session. Thank you. Hi, everyone. Just to let you know, you have 1 hour for lunch.
Hein? Hein? Alors, qu'est-ce qu'elle a? À consultation. Ah, d'accord, 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 d'accord. Tu es un médecin ici, quoi? Ah, d'accord, d'accord, d'accord. Attends, machallah, machallah, je suis dans un congrès là, un peu international. Hein, jusqu'à demain, je te rappelle tout à l'heure, je te rappelle tout à l'heure, je te rappelle tout à l'heure. Mais tu loges où? Tu es où? Tu es où? Tu loges où? Appelle-moi avant de venir à Dakar, je cherche quelque chose. D'accord, Gueltapé n'est pas loin de moi. On se rappelle tout à l'heure, on se rappelle tout à l'heure, Wallah. Merci à tout à l'heure.
Vous aussi.
Ah, tu l'as collé sur le bureau?
Oui, bien sûr.
Il est en haut.
Copie, donc c'est copie. Coller.
Après, tu l'enlèves, hein. À la fin de ta communication. À la fin de la com, tu enlèves ça. À la fin, à la fin de la com,
C'est pas grave, c'est pas grave. Déjà publié ça.
Hein? Déjà publié? C'est ce que tu viens de publier, non?
Ouais, non, non, non.
Ah, c'est déjà fait? D'accord. D'accord.
Expérience.
Ah, super, les graines.
Ouais. Ah. Ah ouais, attends, parce que je dois lire. Donc je vois.
Le pointeur, il n'est pas là, hein, vraiment. Tu peux te soir relire. You can read it in English. C'est la dernière session des plénières, hein, je crois bien. C'est la dernière session, c'est les dernières sessions des plénières.
Ouais.
Après toi, il y aura.
Quoi?
À ta fête. Après toi, il y aura 2 autres, je crois bien.
Ouais, 2.
2, hein?
Je vais juste lire doucement et après. Comment tu trouves ma.
Non, 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 les diapos sont belles. Les diapos sont belles. Ouais, ouais, les diapos sont belles. Machallah, ça, c'est paysan. Comment dirais-je, cellule d'acide composition.
Je vais mettre là, IDD. Ah, c'est pas la peine de parler des publications, s'il vous plaît.
D'accord. Ne pas. Je me limite à ça. Moi, j'ai même en tête le reviveur, comme ce que j'ai fait. Moi, je suis viveur dans un journal américain, ça, c'est quelque chose. Tiens, j'ai bien, la valorisation, c'est bon.
Ouais, on a beaucoup de choses. Mais le problème, c'est ils me donnaient l'ok de parler en français. Je ne vais pas m'arrêter. Je ne vais pas m'arrêter.
Ne pas en français. Your slides are in English. All your slides are in English. So you can speak in. J'aurais dû amener exactement mon pointeur, celui que j'avais hier. Mais dans tous les cas, il y a un pointeur. Attends, c'est un pointeur. J'essaie de. D'accord.
OK. This is the argan oil quality, this study. Das liegt bei uns in Mathematik. Very fast, then oxidation information. To this, we have this 3D. Alors, also that already we nitrosamine. The fifth is brown. So from this,
Tu commences par boire.
il est en train de me...
Bien boire, hein? Il est en train de le chercher. Tu bois bien avant de démarrer. Plus tu bois, plus...
Non, je dois chaque fois.
Voilà. Alors, Ibrahim, wow, descends demander à Prof Matar ou à Prof Modou le pointeur. Prof Matar. Ou bien Prof Modou qui a le pointeur. Mais c'est pour Prof Saïd qui voudrait vérifier pour ces Japon. Avant que les gens... Il n'est pas là-bas parmi les gars là. Ça, c'est vraiment super. Les graines. Hein? Hein? Vous êtes en haut, ça? Ah, nous, on est en haut. Moi, je suis en haut aussi. Mais bien sûr. Hein?
Allez, allez.
Ah, ils sont partis.
Là.
level for sessional depth. Oh.
5 à 6 minutes, 5 à 6 minutes, et je vais animer une vidéo. Tu peux l'animer maintenant. Ça. Voilà. Alors.
Donne-moi la vidéo ici pour le sortir.
Ça ne marche pas. Non, ça ne marche pas. Ah, ce matin, il y a une...
Allô?
C'est pas nous qui gérons ça.
Good afternoon, ladies and gentlemen. We are not far to the end of our Congress. This session will be animated by the Professor Said Garbi. Said Garbi is an associate professor of analytical chemistry and quality control at the Polydisciplinary Faculty of Taroudan, Ibn Zor University of Morocco. He received his FID in analytic chemistry and quality control from the Faculty of Science and Technology of University Mohammed Fayez Rabat in 2012. He is currently head of research for the biotechnology, analytical science and quality control. He worked in the food industry at Lecher, Crystal, between 2004 and 2011 in Casablanca, Morocco, and after at the Ministry of Agriculture, Autonomous Establishment of Control and Coordination of Export, currently known as Morocco Foodex, between 2011 and 2018. He is head of research in analytical chemistry and quality control, valorization of medicinal aromatic plant, oil science and technology, food analysis and biochemistry techniques, biochemistry and agricultural chemistry. Mr. Garbi will present in French. Thank you, Mr. Garbi.
Thank you, Mr. President. Hello, everybody. I'm very happy to be here and to be here with you and take part of the important event about chemistry level for the sustainability development of African countries. Et enfin, j'ai préparé mon speech en français, mais les diapos seront affichés en anglais. Je vais aller doucement. Et si vous avez des commentaires ou des questions en anglais, je suis là. Donc, ma présentation intitulée le rapport de la science analytique pour le développement d'un arbre endémique au Maroc. Et d'ailleurs, vous avez la même chose ici au Sénégal. D'accord? Alors, pour vous présenter ce travail, donc, j'ai choisi le plan suivant. Il est réparti en deux grandes parties. La première partie, c'est des généralités sur l'arbre l'arganier et l'huile d'argan et les méthodes d'extraction de l'huile d'argan. Ensuite, la partie la plus importante, c'est le rapport de l'université, de la recherche scientifique pour le développement d'un arbre sauvage, un arbre endémique au sud-ouest du Maroc, où je vais
parler sur 3 sections. La première section, c'est par rapport à la recherche fondamentale, c'est la connaissance de la biomasse, la composition chimique de toutes les parties de l'art gagné. Après, on va passer à une partie très importante, c'est la recherche pratique, où on a valorisé les molécules bioactives qu'on a identifiées dans la première partie dans des produits cosmétiques. Et finalement, la troisième section, c'est la partie la plus importante qui manque les chercheurs. C'est le transfert technologique du laboratoire vers l'industriel, vers les coopératives, vers la création des startups. Voilà. D'abord, qui ne connaissent pas l'art gagné, c'est un arbre unique au Morocco. Il est endémique au sud-ouest du Maroc. Il représente la deuxième réserve forestière au Maroc. Il s'adapte au climat aride et aride, this tree grows in arid and semi-arid area. Et on parle de plus de 21 millions d'arbres étalés sur 800 000 hectares. D'accord? Donc il peut vivre jusqu'à 200 years, et il s'adapte à des températures très élevées, donc de 3 à 50 degrés C. Alors, généralement, cet arbre, il donne des fruits, de petits fruits de différentes formes, comme vous voyez ici, ovales, sphériques, fusiformes, de différentes formes. Et chaque fruit, il est constitué de la pulpe, voilà, la pulpe et la noix. La pulpe, c'est une matière très très riche en protéines, d'accord, et la noix. Et à l'intérieur de cette noix, c'est une matière très dure. On trouve quoi? Les amandons, les kernels. Donc les amandons. Et dans ces amandons, on trouve le fameux produit, c'est l'huile d'argan. Donc les amandons contiennent jusqu'à 55% en huile. Et croyez-moi, alors c'est un arbre multi-usage. Ça veut dire quoi multi-usage? C'est-à-dire qu'on peut utiliser toutes ces parties. Donc par exemple, on peut utiliser le bois et les noix pour la production de l'énergie, pour la formulation et la fabrication du charbon actif également, et les feuilles et la pulpe pour l'alimentation animale. Et finalement, les amandons pour la production de l'huile d'argan. Alors, maintenant, depuis longtemps, l'extraction de l'huile d'argan était traditionnelle, c'est-à-dire par des méthodes traditionnelles. Et la femme, c'est un travail de femme, donc pour extraire cette huile, pour extraire 1 litre de l'huile d'argan, il doit travailler plus de 20 heures. Donc, le procédé il commence comme suit. Généralement, le procédé d'extraction est constitué de 6 étapes. Donc, après la récolte, drying, c'est séchage. Donc la première étape, c'est le dépulpage. Ça veut dire quoi le dépulpage? C'est-à-dire la femme doit séparer la pulpe et la noix. Alors que ce travail peut être effectué parfois par l'animal, par les chèvres. Parce que les chèvres, elles mangent la pulpe, ils laissent la noix. Après, on récupère la noix. Il vient l'étape suivante, c'est le concassage, et d'ailleurs c'est l'étape la plus pénible. La femme doit concasser la noix pour libérer les amandons entre 2 pierres. Comme vous voyez ici, le résultat c'est quoi? C'est le coq pour la production du charbon actif et les amandons pour la production de l'huile. Ensuite, on passe par la torréfaction pour produire de l'huile d'argan alimentaire. Parce qu'il y a 2 types de l'huile d'argan alimentaire, food grade and cosmetic grade. Alors pour l'huile d'argan alimentaire, donc on doit passer par la torréfaction. Ensuite, le malaxage, où la femme ajoute une petite quantité de l'eau tiède pour faciliter la séparation et l'extraction de l'huile. Et finalement, on passe à la dernière étape, c'est la moins 100 € le litre. Donc, il y a des personnes qui mélangent cette huile avec d'autres huiles végétales pour gagner plus. Alors nous, en tant que chercheurs, et pour arrêter ces pratiques illégales, nous avons préparé dans nos laboratoires plusieurs mélanges, comme vous voyez dans cette diapositive, avec argan with soybean oil, rapeseed oil, sunflower oil. Donc on a mélangé plusieurs argan avec plusieurs huiles, exemple soja, tournesol et le colza. Et on a cherché quels sont les marqueurs pour dire, voilà, tiens, l'huile, elle est falsifiée. Et finalement, nous avons élaboré un arbre de décision. C'est-à-dire le laboratoire, et d'ailleurs ces résultats sont très utilisés maintenant dans les laboratoires marocains. Alors, on commence par l'analyse du zinc saponifiable. Si on trouve une teneur supérieure à 2%, on dit, tiens, l'huile d'argan, elle est mélangée par l'huile minérale, c'est l'huile de moteur, l'huile des voitures. Alors, sinon, on passe à une autre analyse par la chromatographie en phase gazeuse pour déterminer le profil en acide gras, et on cherche le fatty acide 683. L'acide gras 683, c'est l'acide linoléique. Normalement, l'huile d'argan ne contient pas de 683. Et si on trouve une teneur supérieure à 0,3, on dit, tiens, l'huile, elle est mélangée par rapeseed and soybean oil. Voilà. Et sinon, on passe à l'analyse plus approfondie, c'est l'analyse des phytostérols. Avec la même machine, c'est avec la chromatographie en phase gazeuse, avec un détecteur FID. D'accord? Et on cherche directement la teneur en compostérol. Si on trouve une teneur supérieure à 0,4, on dit, tiens, elle est vraiment mélangée avec. C'est une deuxième confirmation. Et pour vérifier est-ce qu'elle est mélangée avec l'huile raffinée ou l'huile vierge, on peut passer à une analyse qu'on appelle les stigmas stadiales. Donc la limite, c'est 0,15 mg par kilo, c'est ppm. Voilà. Et vu l'importance de cette étude de l'adultération, il y a plusieurs chercheurs qui ont travaillé dans cette thématique en utilisant d'autres marqueurs. Je cite par exemple le travail des chercheurs marocains là. Ils ont utilisé les polyphénols, d'autres équipes ils ont utilisé les hydrocarbures, une autre équipe a utilisé l'huile minérale, les triglycérides, les tocophérols et ainsi de suite. Voilà. Alors, un sixième projet sur le raffinage. D'abord, c'est quoi le raffinage? Le raffinage, c'est un processus industriel. Il y a, dans le monde, il y a le raffinage physique, raffinage chimique, en utilisant des solvants, des solvants organiques ou des composés organiques, chimiques, pardon. Et il y a également du raffinage enzymatique, en utilisant des enzymes. Nous, on a choisi un raffinage physique, sans utilisation des produits chimiques. Alors, d'abord, on ne raffine pas de l'huile de bonne qualité, on raffine seulement des huiles de mauvaise qualité, c'est-à-dire de valoriser quand même les huiles qui sont déjà dégradées. D'accord? Normalement, la question c'est les avantages et les inconvénients de raffinage de l'huile. Effectivement, il a des avantages et des inconvénients. Parmi ces avantages, est que le raffinage, il élimine presque tous les impuretés de l'huile et les composés d'oxydation, mais il a également des inconvénients. Alors, les inconvénients de raffinage, c'est-à-dire qu'il élimine une grande partie des molécules bioactives. Et ça, il influence directement sur la stabilité de l'huile. Donc, c'est-à-dire, lorsqu'on raffine l'huile, on améliore la qualité commerciale, mais sa stabilité est diminue. Donc, normalement, il mérite une attention particulière, une conservation dans des bonnes conditions. Et le dernier projet pratique, c'est la valorisation du coût-produit. On allait vers la valorisation du coût-produit, genre les feuilles, les tourteaux, la pulpe et le coq. Donc, l'idée de ce projet, c'est extraire des molécules bioactives, genre les antioxydants, les polyphénols par exemple, et enrichir l'huile qui sont trop sensibles à l'oxydation. L'exemple, par exemple, les huiles commercialisées dans le monde, c'est l'huile de tournesol raffinée. Donc l'idée c'est quoi? C'est de remplacer, parce que les industriels, qu'est-ce qu'ils font? Donc pour stabiliser leur huile, qu'est-ce qu'ils font? Donc ils ajoutent des antioxydants synthétiques, comme l'exemple du BHA et le BHT. Alors ces antioxydants sont néfastes pour la santé. Donc l'idée c'est de remplacer les antioxydants synthétiques par des antioxydants naturels issus des coproduits de l'arganine. Et finalement, la dernière partie de ma présentation concerne le transfert technologique, c'est-à-dire le transfert du laboratoire vers la coopérative. Donc, ce processus a été initié depuis l'année 1995. 1995, on a créé la première coopérative. Maintenant, le nombre de coopératives au Maroc, c'est 850. 850 coopératives. Donc, d'abord, on a commencé par la création des coopératives, la formation du coopérative par rapport à tout ce qui est gestion de coopérative, les droits d'entreprise, la gestion de la coopérative, et également la replantation pour le conserve de la biodiversité, la replantation de cette plante. Et également des formations sur les bonnes pratiques de fabrication, c'est-à-dire quelles sont les bonnes pratiques qu'on doit suivre pour produire une huile de très bonne qualité qui répond aux exigences des normes internationales. Aussi des ateliers pratiques. Comme vous voyez ici, nous avons organisé un atelier pratique à notre faculté au profit des coopératives. On a invité 100 coopératives et on a les formés par rapport à la formulation des produits cosmétiques au laboratoire de notre université. Voilà, comme vous voyez ici dans cette photo. Voilà. Et également, nous avons accompagné plusieurs coopératives pour l'obtention des certifications de conformité par rapport à des normes internationales, des normes de sécurité alimentaire. Exemple, Food Safety Management, l'IFS, International Food Safety, et le BRC. Donc, maintenant, il y a plusieurs coopératives bien structurées ayant des normes qui répondent aux exigences des normes internationales. Voilà. Et le résultat de tous ces efforts, passant de la recherche fondamentale, la recherche pratique et la recherche d'action, donc comme vous voyez, l'huile d'argan, l'économie de ce produit a connu une réussite vraiment très marquante, en passant en 2005 de 80 tonnes d'exportation à 1950-60 tonnes en 2019. Et le prix de l'huile d'argan a passé de 5 € à 100 €. Et ceci grâce, croyez-moi, à la recherche scientifique et grâce aux chercheurs. Alors, voilà, donc, et je pense que vous avez votre pays est très riche en plantes médicinales. Et vous avez un arbre très similaire à l'arganie. C'est là le tougar, le bananetis et le palmier du désert. Voilà. Alors voilà, avant de rendre la parole à Monsieur le Président, donc je remercie mon ancienne équipe sous la direction de mon professeur Zubida Sharaf, c'est elle qui a initié la recherche sur l'arganie, et ma équipe de l'université Ibn Zor. Alors, et merci de votre attention. Et je suis là pour si vous avez des questions.
Merci, professeur Saïd, de ce brillant exposé dont vous venez de nous gratifier et qui, en fait, là, un peu fait le bilan de l'argan depuis pratiquement la récolte jusqu'à la valorisation. Valorisation par rapport à l'alimentation, valorisation par rapport aux cosmétiques. Et en plus, il y a quelque part un service à la communauté. À la fin de la valorisation, ce service-là prend en compte un peu les communautés locales. Je crois que c'est un exemple à méditer chez nous. Sortir un peu des labos, trouver des choses, mais essayer de les expliquer aux populations dans le cadre en fait du service un peu à la communauté. Thank you, Mr. Garbi, with your presentation. Je présente from the harvesting until the valorization. With addition in some entertainment with the local population. Thank you, thank you, thank you, and thank you very much. And we can now open some questions. Oui, question?
Voilà, merci pour votre présentation qui a été très détaillée et j'ai très bien apprécié. Par contre, j'ai deux petites questions. Bon, la première, j'ai vu quand vous faisiez votre introduction, vous avez parlé des HAP. Bon, mais je n'ai pas vu ça. Bon, je ne sais pas, est-ce que vous avez analysé ça ou pas. Bon, l'autre chose, c'est que ici au niveau du Sénégal, donc, il y a une réglementation quoi, sur l'huile alimentaire, c'est-à-dire qu'il faut que cette huile-là soit fortifiée en vitamine A. Bon, je ne sais pas maintenant, bon, j'ai vu que vous avez fait beaucoup d'incorporation, d'enrichissement, je ne sais pas maintenant avec la est-ce que vous avez fait, si oui, quels sont les résultats escomptés? Merci.
Merci. Merci pour deux questions pertinentes. Donc, par rapport à la première question, l'analyse des HAP, en fait, l'origine de l'HAP, c'est les hydrocarbures aromatiques polycycliques, c'est au niveau de la torréfaction. Le grand problème, lorsqu'on torréfie il y a le risque de la formation des HAP. Alors, effectivement, nous avons fait plusieurs tests pour déterminer quel est le temps et la température optimale pour ne pas former, parce que le Codex Alimentarius, il a limité le seuil des HAP à 2 nanogrammes par kilo. D'accord? Donc, on a fait des HAP par HPLC, d'accord? Pour vérifier le temps et la durée de torréfaction. Alors, si j'ai bien compris la deuxième question, donc la vitamine A, donc l'huile d'argan, naturellement, elle est très riche en vitamines. Donc, il contient jusqu'à 900 ppm de vitamines. C'est la vitamine E. La vitamine E, il a un pouvoir très intéressant en termes de stabilité par rapport à la vitamine A. C'est vrai que les industriels, ils ajoutent la vitamine A et la vitamine D. C'est question pour les gens qui en manquent de vitamine D. Mais nous, on parle de ce qui est naturel. L'huile d'argan, c'est antioxydant naturel. Et merci.
Second and last question.
Ok, merci beaucoup pour votre présentation. Vous avez là un projet très ambitieux. Et donc, félicitations pour ce que vous avez déjà pu faire. Alors, moi, j'ai quelques petites questions concernant notamment la partie où vous essayez d'enrichir l'huile avec des extraits pour stabiliser aussi. Bon, vous parlez de 3 types d'extraction. Je ne sais pas, est-ce qu'après l'extraction, vous faites un screening pour évaluer les toxicités, les teneurs en différents groupes, avant donc de valider quelle fraction, dans quel solvant faut-il valoriser dans l'huile, parce que là, ce n'est pas ressorti. Donc ça, c'est le premier point. Deuxièmement, est-ce que, vu tout ce que vous avez pu faire, est-ce que le coût donc de tout ça, à la fin, votre huile, le prix par rapport à l'huile rafidique commerciale, comment est-ce que vous évaluez votre huile? Est-elle plus chère? Moins chère. Et également, vous avez parlé donc des antioxydants synthétiques qui sont ajoutés. Oui, les antioxydants ajoutés que vous jugez dangereux, est-ce qu'il ne faut pas un peu relativiser? Parce que peut-être ça dépend de la dose qui est admissible. Merci.
Merci. C'est par rapport à ta première question concernant la toxicité des plantes. Nous, on travaille par l'approche participative, c'est-à-dire plusieurs équipes. Chaque équipe est là, sa discipline. Nous, en tant qu'analyticiens, donc on travaille avec l'équipe de la biologie qui nous renseigne sur la conformité de chaque plante. Puis, nous, on fait varier la concentration, mais quand même, on ne doit pas dépasser la concentration des antioxydants synthétiques. Parce que, par exemple, j'ai le BHT ou le BHA, le Codex Alimentarius. Donc, moi, je suis un auditeur qualiticien. Donc, je fais des audits dans ce sens dans l'industrie alimentaire. Donc, on ne doit pas dépasser les 200 ppm. Et du coup, nous-mêmes, on ne doit pas les dépasser. Pour quand même, on compare nos antioxydants par rapport les antioxydants synthétiques. Donc, d'abord, ça c'est pour la première et la deuxième question. La troisième, c'est par rapport à quoi après chaque stade, après chaque étude, après chaque étude, on fait plusieurs analyses. On fait même des analyses organoleptiques, sensorielles. Parce que quand même, le produit, il va être consommé. Donc, on fait même des analyses sensorielles pour déterminer l'acceptation. Parfois, on invite des consommateurs comme ça, aléatoires. Alors, s'il vous plaît, ton appréciation par rapport à ce produit. Est-ce que tu peux l'acheter? On fait même des tests consommateurs. D'accord. Par rapport au coût, effectivement, le raffinage égale un coût de plus. Mais l'avantage du raffinage, on raffine des huiles de mauvaise qualité, des huiles marginalisées. Parfois, comme je vous ai présenté dans les premières diapositives, parfois l'animal, le chèvre, il participe dans le processus d'extraction de l'huile. Mais malheureusement, il laisse des odeurs, des mauvaises odeurs à l'intérieur de l'huile. Et les gens n'acceptent pas ce genre d'huile. Et du coup, pour valoriser cette huile, on passe par un raffinage. Et heureusement, le domaine cosmétique, il préfère des huiles raffinées. Pour des préparations cosmétiques, il préfère des huiles raffinées transparentes. Voilà. Et merci.
Alors, on applaudit encore le professeur Saïd. Hein? Merci. Ça marche.
Merci beaucoup.
Ça, est-ce que and how much USB port do you have? Okay, you have 3 of them. Okay. The other side, there are no USB port. USB-C. Oh, oui, mais ça gêne, tu sais pas, ça ne fera pas. So you will not be able to use this device then.
Ouais, c'est bon. If you are ready. Okay.
Hello, ladies and gentlemen. We are pleased to welcome Mrs. Shaima Ekel. We will present us a speech about Elsevier solution for advancing chemistry education, and chemistry research. Mrs. Shaima Ekel is an expert in life science. Her current role is on developing and expanding Elsevier partnership. She has lectured more than 300 workshops and seminars on research topic, tools, publishing, writing ethics in relation with many governments. She has a strong academic background. She holds a bachelor in pharmacy, 2 masters in biotechnology and public health. And currently, she is a PhD candidate at the American University in Cairo. So, Mrs. Shaima, you have the floor.
Thank you. Good afternoon, everyone, again. I hope you're enjoying the conference and you're excited at the last day. Today, we wanted to talk with you about Elsevier solutions and how we are supporting chemistry research and education. First of all, before I start, I wanted to give you an overview about Elsevier because mostly, or maybe many of you will know Elsevier as a publisher, but Elsevier is now transforming to an analytics business company. So we're providing tools and solutions, databases and so on, to researchers, to support researchers in all the steps of the research and the publishing process. So from the step, you start to think of an idea to work on for your research, and going through all the steps until you reach the step of publishing your manuscript, and even beyond that for the visibility of your manuscript and so on, we have solutions that can support you in each step. So when you search for an idea, when you try to find the gap of any topic, when you have an idea already and you want to find how to design your study, how to design your methodology, how to find the information in the literature, how to write, how to publish, all of this we can support you in. Yeah, this is how it looks like. So we have many solutions and databases that can help you. But we came here mainly for the life science solutions we're having. We have many solutions specialized for the life science fields or departments, including Reaxys, which is a chemistry database that would be relevant to most of you or to all of you, and also Embase, which is a biomedical literature database that might be of interest to some of you who are working in relation to the medical field. Okay, this was an overview about Elsevier and what we're trying to do. And then, before we start our Reaxys demo, I wanted to get a quick introduction from you, or lesson to you. What are the challenges that you might face in your research, or what kind of databases you usually use for doing your research, for designing your studies, for getting information and so on? Just to know a quick idea of what you face in terms of challenges and so on. Yeah. No? Any input? So let me ask it differently. Do you have this problem of that you have an idea in mind, but you don't know how to find the information, or, right? It's a challenge everywhere. What else? Do you face the problem is that you have some information, but you don't know which one to trust? Right? What else? Right. Sometimes you have the idea, but you don't know where to find it. a great one as well. Sometimes you know you have a great idea, but you're not sure if anyone worked on it before or not. Yeah, many challenges, I know. So, yeah, I tried to summarize some of the challenges related to the information or finding information. We know that the life science researchers usually have many challenges, but related to the things related to their productivity, that reduce their productivity, is that you're trying to find information, you're trying to find a good research plan or design a good research plan, and then you have this problem of finding grants for your research, writing grants, and then you're trying to track and monitor what's there in the literature, and now things are advancing very, very fastly, so you're trying to cope with this, and then you also need to find new ideas, you need to find collaboration to try to handle the problems that you don't have some machines or some materials, so you need the collaboration. So we have many things that sometimes affect our production, and that's why we as Elsevier, we're trying to collaborate with many of you, we will hope to collaborate with all of you so that we can support you as much as we can in solving these challenges or these problems. Yeah, one more thing to say is that we did a survey with researchers in the life science field before, and we were trying to understand the problems that you are having while searching for information. And then we got more than 50% of the chemists who answered the survey reported that they at least have to search the literature for more than 5 hours per week. So that's too much, and you can invest, if you're having something that would ease the way of searching for information or finding information, you can use this time for your research and do your experiments and then perform more or publish more and so on and so forth. And here comes the importance of Reaccess, our database that we're going to walk you through it today. So the idea is that Reaccess is a specialized tool in the chemistry field that would help you as much as possible decrease the time that you're investing in searching for information. Instead, it will help you also use the information you have directly. So it's not about searching for information and then trying to read and then trying to extract the information and then you start work with them. No, it's more about finding the information in a way that you can use them directly without, so the extraction and the collection and everything is done already for you. So you use your time better. So what's the Reaccess? Reaccess, as I said, it's a chemistry database, and it's been developing since 2009. Reaccess is provided by Elsevier, and throughout the years, Elsevier has been developing Reaccess a lot by adding more information, more modules, more technology, investing in technology to support chemists as much as possible. So, for example, we've added many collections in different languages to the content of Reaccess, and then we've added the medicinal chemistry module because we know many of the chemists are working also in bioactivity data and in drug discovery and so on. And then we added a module for the retrosynthesis to also help researchers use the AI to not only find the routes for synthesis that were published before, but also try to predict new routes using the artificial intelligence to start synthesizing your compounds and many more. So we're trying to invest as much in the technology to support the researchers at the end. What we have so far is one solution that includes more than 6 databases. So Reaccess now includes a substance database where you will find more than 283 million substances available with all the properties. And this is by far the most comprehensive database available, with like more than the double of any other database in chemistry. And then you have access to all the properties of the substances you're trying to search for or of interest to you. And then you have also the bibliographic database. So if you're interested to find articles and patents, you have access to that. And the patents, by the way, are coming from 105 patent offices worldwide. And everything is translated manually. So you're 100% sure that the translation is accurate and you get full access to the claims of the patent. And then, if you don't want the articles, you want directly to draw a structure or to write a name of a substance, and you find the data on the substance, you can do that. You have the substance database, and you can access the properties directly from Reaccess. And then we have one more database, that's the bioactivity and target database, and this one is designed also to help any of the chemists who's working on a substance or a molecule that has bioactivity data. So even if you're not a medicinal chemist, but you're a chemist and you're working on a molecule that you need to check the toxicity of, or what was the studies that were done for its assessment, or characterization and so on, you can also use the bioactivity and target database. And at the end, we have also the predictive retrospective tool that, as I told you, it uses AI to help you finding all the routes of synthesis that were published before for your compound, but also to use AI to predict new routes for synthesizing this compound. And we talked about this in our session of green chemistry, because it's very helpful for researchers who work in green chemistry. So at the end, the idea of Reaccess is that you're not searching to find information. It's showing you the information in the way that you can use it directly. So I will show you in the demonstration, but you will have tables with all the information extracted from the source, so you don't have to go to the full text and read. You have the information in front of you, and you just go and use them directly, and you have the sources if you want to cite the reference in your article. A little bit also info tips about how or where the indexation is coming. The information is indexed in Reaccess. So Reaccess is indexing all the articles that are related to chemistry. So all chemistry and chemistry related fields. So even if you want to search for any concept that's not a chemistry concept, you can do that on Reaccess, searching for nanoparticles, for cardiac arrest, for any keyword that's related to the chemistry field. You can do that on Reaccess, and it's indexing from also all the publishers, so all the publishers are covered. And you have access, as I said, to the bibliographic records, to the substance records, and also to the reaction records. The indexation itself or the keywords that you can use are coming from different databases in different fields. So you have the keywords in Reaccess, the chemistry keywords. You have the keywords in Embase, which are the medical keywords. And then you have also the engineering keywords, the geology keywords, and the bibliographic keywords from Scopus. So you can search with any keyword and you will find your articles directly. How to search on Reaccess is now also being super user-friendly, because you can ask Reaccess any question in your mind. So you can go to Reaccess and then type a text, search for a keyword. Or you can draw your structure and search for your drawn structure. Or you can write the chemical name of the compound. Or you can ask a question related to a reaction or related to a target, and then Reaccess will identify the kind of question you're asking or what you want to search for, and then will show you the results in this way. So if you search for a substance, you will get substances and you will get documents. You will get the commercial availability of the substance. If you search it for a reaction, you will get the reactions. If you're interested in a medicinal molecule, you will get the targets and so on. And then you also have like more advanced way of searching, because sometimes as chemists we have some information, pieces of information, but we don't know the type of molecule, for example. Like I extracted a molecule from the water and I did some testing. I have the spectral data I have the molecular weight. I have some information, but I don't know what's the molecule. So we have in Reaccess a module called the Query Builder. The Query Builder is the advanced search, but in a user-friendly way. So we have more than 500 fields listed, and you can choose from the list what fields what information you know, and then you start to enter the information you know, and then you go search for your substance or for your reaction and so on, and it will show you based on the information you input what the output should be. So yeah, this is the idea. Reaccess is trying to support chemists in all the steps they are doing in their research work, from the start for finding an idea or for writing a research proposal, till monitoring the research design and the work, till analyzing for all of the researchers here are working on analytics or analytical chemistry, analyzing the molecules and then writing and publishing their articles. This was a brief introduction about Reaccess, and now let's go to Reaccess and do a practical demo on this. Okay, so here is Reaccess. And this is the home page, and as you can see, the coverage is transparently shown in the home page. And it gets updated very regularly, so you know like what's covered and how many substances, reactions, bioactivity data we have. And as I told you, for example, the bioactivity data is more than double any other database available. So the coverage is by far the most comprehensive coverage for a chemistry database. What we can do in the Reaccess, as I told you, so you have first the quick search, and then the query builder, which is advanced search. And then you have the retrosynthesis module if you're interested to do any retrosynthesis plan. In the quick search, you can search with any keyword in mind. So I can write here any keyword, cardiac arrest, nanoparticles, any keyword, but because it's a keyword, we will directly get the documents. So if you wrote a keyword that's not a chemical substance, you will get directly the documents. If I want to search for a chemical substance, a compound or a substance or a molecule, you can write the name of the compound, the CAS registry number, the smiles of the compound, the chemical name of the compound, or you can draw the compound from here. And then from here, we have the structure editor, which includes Marvin.js, that's designed for Reaccess, or ChemDraw, if any of you is familiar with ChemDraw or use ChemDraw. So you can draw your compound also from here. Let's start like with a basic thing or an easy example. So for example, searching for coumarin. You know coumarin, of course. So if I wanted to search for coumarin, Reaccess will identify coumarin as a substance or a molecule, and it will show me the data as substances, all the substances related to coumarin. So coumarin and its derivatives and subderivatives, and then all the documents talked about coumarin. Of course, it's a broad search, so we have 92,000 articles, and then the commercial availability of the substance. This one would be important if you're searching for a molecule that you're going to use in your in any preparation or reaction, because you can identify the vendor of the molecule, and then you start ordering your compounds and so on. Let's check the substances we got. So we have 546 substances, coumarin, and all the derivatives and subderivatives available. And for each one, you have here all the properties reported about the compound. So if I went to the identification, it will show me the molecular formula of the compound, its molecular weight, and so on. And then you have the substance label, you have the derivatives, you have related structure, patent-specific data, so everything related to the identification of the compound. And then you get also the drug likeliness. The drug likeliness will show you info about how the 5 rules of Lipinski would apply to this compound. So you understand if this compound is having any medicinal activity and so on. And it's here, of course, because coumarin can be used as a medicinal molecule, or it has some bioactivity data. So you already have the data here, and it will show you the rules of Lipinski. And then let's start with these first. So you get also all the physical data reported about the compound. And here you can load more, I mean, to forever. So the melting point, for example. Everything, when you go to the melting point, it will show you a table where all the resources that reported melting point for this compound is there, and then the melting point, the number itself is extracted from the article. So you don't have to read the article, you know already. And then, of course, you as a researcher will decide which one to use or which range to use based on your experience. But you have all the information in front of you. This applies for everything. So melting point, boiling point, association, adsorption, crystallography, everything. And you can keep loading more to see all the data. Electrical data, dielectrical constant, energy, dissociation energy, and so on. And then, so these were the physical properties. And then you get also the spectral properties. So if you're interested in NMR spec or IR or UV, so you get also all the information in the form of a table, and everything is extracted from the table in front of you. And then you have also the link to the source if you want to cite the source, or to check the full text of the source if you want to read more. Here also you can load more to find all the spectral data. And then at the end you also have the other data. And then the other data, you get everything else that was reported. So if this molecule is reported to be a contaminant in the environment, it will show you what was, where it's located first, where it's located as a contaminant, what was the contamination concentration, and so on and so forth. And then if it has any use reported, you will get the use. If it's isolated from a natural source, you also get the source it's isolated from. So everything. And then the one we didn't do, that you get also, because this compound is also used medicinally, so you get also all the bioactivity data of the compound, which is here. When you go to the bioactivity data, you will find everything that was reported in studies that efficacy of the compound in vivo or in vitro, and then the metabolism studies, the pharmacokinetic studies, and the toxicity studies. And everything is also in the form of tables. So if we went to the in vitro studies, you will find the table showing you the study, what they were trying to measure. So here they were trying to measure the IC50, what was the value they got, what was the action on target they got, what was the target our molecule worked against, and so on. If they used any cell line, you will find the name of the cell line here. If they used any cell line, you will find the name of the cell line. If they used any other in vitro model, you will find it. And then you also get the information in the source of qualitative results. So here you have the quantitative results with the numbers, and then you have the qualitative results showing you just the action and the effect and so on. This also applies for the in vivo studies. For the in vivo studies, you also get the animal models they used, what was the dose they used, the route of administration, so everything. And everything is extracted for you. And this applies to the rest. Like you can get info about the metabolism, the toxicity, the pharmacokinetics, everything that was reported before. So this was a toxicity studies. At the end, if you're interested in this bioactivity data, what you can do, so now we have 546 compounds related to coumarin and subderivatives and derivatives. What you can do is that you can create a map with all these derivatives and all the targets they work against. So if we went to this bioactivity visualization, you will find coumarin and all the structures we had, and all the targets that they work against, and the potency against each target. And you can navigate the map. You have a navigator here to go from one side to one side, and you have a legend to show you what the colors mean. So here it's telling you towards the green, it's a higher potency, and then lower potency, and so on. And this map, by the way, is used for the SAR analysis. I'm not sure if any one of you is doing SAR analysis, but this is a map that can be used for SAR analysis later on. And in all the steps that we did, you have also the option to export your data. So you can export any data you get in Reaccess to a PDF, to an Excel sheet, to have them stored in your laptop, and then you can work on them offline later on. Okay, let me go back. I also wanted to show you this because so now we have 546 substances. Maybe you're not interested in all of these. You only have one derivative in mind. So we have the filters here, and the filters are dynamic. So they change according to the category of results you're in. So because we're in substances, all the filters are related to substances. So you can here filter to the target you want the substance to work against. You can filter to a structure of the substance. You can filter to the substance class or the molecular weight of your substance. So you can tell it, okay, I don't want the 500 substances, I only want the molecules that are that have molecular weight between 144 and 156. You can filter to the number of fragments, to the availability, and then you have also the bibliographic filters. Okay, let me go back and let's try searching for something else. So let's try to search for a reaction. So for searching for a reaction, you have also many options. You can type here, send a preparation of something or reactions of something, or you can go to the the structured editor, and then you draw your reaction yourself. Let's try it from here, so you know also the structure editor. So the structure editor is having all the tools that you would want to draw your compound. And this one is used to check the novelty of your compound. So if you have a new compound, you can draw it here and then start to searching for it to make sure that if anyone worked on this compound before or not. And when you search, when you draw a compound here, it will search for it as drawn or as substructure or as similar. So it will help you finding if your product or compound is novel or not. Now, if I want to find the reactions of coumarin, for example, I can also insert the structure from name because it's already a known molecule. So I can go to here and then type coumarin. It will draw coumarin for me, and then based on what I want, I can add the arrow to define what kind of reactions I want. Do you want the reactions where coumarin is the end product, or do you want reactions where coumarin is the starting materials? Let's search for this. So now I'm searching for the reactions where coumarin is the end product, and then I will transfer to query and search for that. So Reaccess knew directly that I want the reactions, and I have 350 reactions as for the compound as drawn, and then much more reactions for similar compounds. I will check these reactions, and then you have all the reactions where coumarin is your end product. And then you have all the conditions for this reaction coming from different sources, showing you also the yield that they got and the experimental procedure if you want to apply this in your lab. And then and at the end you can check all the reactions. You have also the filters. If you notice, the filters it changed now because we're in reactions. So you can filter to the yield. So I want only the reactions that produced more than 90% yield, or you can filter to a specific solvent to use, a specific catalyst to use, a catalyst class, a solvent class, and so on and so forth. And then if this is the reaction that you're going to use, for example, you can highlight it and you can also export it with all the data available if you want to apply this to your lab. Okay, let's go back and let me show you also the retrosynthesis. The retrosynthesis, as I told you, is very helpful to show you two things. All the published roots for a compound, and then using also AI for predicting new roots. What you need to do is that you create a project, draw your structure, the structure of interest, or also insert it from name if it's a known compound. So we can search for imatinib, for example. It will draw imatinib, and then I will ask it to synthesize or show me the synthesis ways of imatinib. It will directly show me the published roots, what was already published in the literature. So I have 7 roots for synthesizing imatinib that were published before, and then it will take like 10 minutes to predict new roots for synthesizing this compound. Let me show it to you because I already did it before, this one. So we can go here. And this you can apply for any molecule, even if it's a molecule that you're working on and it's new. So here, the blue ones are the published ones already, and you have all the steps of them, and you can go check the tree view to get more data or more info about this root. And then these are the published roots, and then we have the predicted roots that are predicted by AI. How the AI predicts these, so it starts to get inspired from other similar reactions that were done before on same groups or like similar reactions, and then it gives you these predicted roots. Starting from the predicted roots, you will find also the score. This score is the applicability score. Like how percent this reaction would be applicable in your lab. So when you find it 95%, so it's 95% applicable, and you have 94, 93 until you reach the 60% applicable. So when you try to choose, it's better, of course, to choose the highest applicable ones, so you don't waste your effort and time in the lab. And if we went to the tree view, you can see all the reactions you have, but it will show you the steps to follow. All the starting materials will be commercially available, so you can order them online directly, and you have the commercial data here. And then if you found this one, for example, is expensive for you, you can add one more step to start from one step more and add, like, prepare this one in your lab. And you can choose like how you want to prepare it. So I can add this step. Yeah, and that's how you start from the materials you already have, or it's easy for you to request. And then you have to the right the conditions, suggested conditions for you to use in each step of the synthesis part. Also inspired from similar reactions that were done before. You have the conditions, the experimental procedure, and if you decided to do this, to apply this one in your lab, you can copy the root, or you can also export it to a PDF. And then you have the PDF in your lab showing you the steps, the route, all the experimental procedure, all the conditions, and you can print it, work with it in your lab. If we went back, yeah, let me show you the query builder, because it's also very interesting, and it's an advanced search module, but it's super user friendly, because you have the fields here, all the fields listed in the axis, and what you need to do is that input everything that you have already. So if you want something that's extracted from a natural source, you can add the natural source here. I want the structures isolated from tomato. And then you search for substances. You will find all the substances extracted from tomato. I hope this was helpful. What also I wanted to say is that we have also many materials or ways to support you in your educational processes as well. I will send you the slides so you get these, and thank you. And by the way, if you want to get free access to the tool, just let us know or send us an email, and we will be there to help for your institution.
Thanks, Mrs. Eichel. Sorry? The last one. The last one? Or? So we want to thank Mrs. Shaima Eichel with this interesting and very useful presentation, especially for our young student who already face problem of biographic references. It seems that Reaxis is a very useful tool, not only a very useful tool, but also it seems to be easy to use also. So thanks again, and I think if you have any question or suggestion about this presentation, yes.
Thank you very much for a very nice talk. It's really very helpful and very user-friendly. My question is going to be, I'm working on inorganic materials. So your examples were mostly on molecules, organic molecules. Do you have also inorganic molecules in your system? Okay. Yeah. Very good. Very good. Yeah, thank you very much. Maybe last very quick question. You also told us it's possible to extract the material, but to what extent we can download or extract the documents or the data from Reaxys? Maybe if I need maybe thousands, 10,000s of data, is it really possible to do?
Another question?
No. So thanks again, Mrs. Judge. Thanks to Elsevier. I have a question. The last.
Thank you for your presentation. It's a useful tool. But the first question is the accessibility. I noted that African country, West African country didn't access. You need to subscribe. Yeah. Okay.
It is individual access or institutional access? Institutional. Thanks again. Merci beaucoup. Allez, merci beaucoup.
Le présentateur, il est là-bas.
Qui doit présenter? Il n'a pas l'air. Hein? Ah, c'est une question d'habitude, hein? Il dit qu'il ne voit pas. Je ne sais pas si c'est vraiment ça. La question de poser. Où est la clé? Tiens, clé. Vous n'avez pas de clé. Vous n'avez pas de clé. Bon, vous prenez votre. Vous n'avez pas de clé. Vous avez une clé, vous? Ah, parce que. Si, peut-être. Hein? Je vais essayer Baham. Non, Bile. C'est bon. Li, bon, les fële la. Je pense que ça va être bon. Di nga gis tu verras waaw di nga gis kay ok ma commence xaaral waaw bàyyi ko noonu moom comprendre na ci ginnaaw ngay def voilà baax na nii non Dramé il va s'en sortir.
Parce que c'est surtout pour les filles.
Hein? Micro bi fi ngay wax.
Depuis ce suba là,
Hein?
depuis ce suba.
Waaw, on était là depuis le matin. Il faut mu dem ni. Waaw. Fu mu dem laa xamul sax. Non di nga gis. Ma commencé hein? Ma commencé. Ladies and gentlemen, good afternoon and welcome to the next conference will be the last. And the conference will be given by Dr. Said Jallo.
My name is Atanas Koli, Professor of Chemistry from Cheikh Anta Diop University. And Dr. Jallo is from LabX CAB. LabX means Laboratory of Investigation and Expertise. For a short biography of Dr. Sayer Jallo, I can say that Dr. Jallo is a PharmD from the University of Dhaka. He got his Master of Science in Diet and Nutrition at the University of Châtenay-Malabry in Paris. He got also his PhD in Analytical Chemistry from Paris, in France. Nowadays, he works in analytical laboratory for implementation novel sensitive analytical method using chromatographic separation method coupled to detectors such as fluorescence, mass spectrometry, and so. Now, he is going to make a presentation on a topic entitled Lack of Oxidative Stress Mediated Serum DA Formation, a novel strategy for an ante-mortem diagnostic tool for Alzheimer's disease. So, Dr. Jallo, you have the floor.
Thank you, Mr. Chairman. Thank you very much for this sweet introduction. First of all, let me thank Hello? Okay, thank you. Thank you, Mr. Chairman, for this sweet introduction. And first of all, let me thank all of that who come here in and I think you spend a good time in Dakar. Vous êtes la bienvenue. Welcome to you. Today, we are not going to talk about pesticides. We are not going to talk about electrochemistry. We are not going to talk about crystallography. But we are going to talk about what role chemistry play in diagnostics. And on behalf of the staff of the lab, I will present you today a topic which is entitled Lack of Oxidative Stress Mediated to the Serum DHEA. And this is used as a strategy to set up a tool for ante-mortem diagnostic for Alzheimer's people. And the plan proposed is, okay, thank you. First, we are going to evoke the aim of this plan. Second, we will talk about the background and also the scope of this topic. Third, It's Rama here? Yeah, come on here, please. I'm sorry, I got some vision problem, that's why. Okay. Drame is here? It's okay, I not... The third, I think we're going to talk about materials and methods. It's not clear for me. Okay? And after that, we talk about the result and also the discussion. And in conclusion, we gotta talk about some perspective. I mean, the basis of the future direction. The objective is, as you say yesterday and the day before, you say that chemistry is all. And in every sector, chemistry plays a role. And this is the case of the topics today because chemistry is not well used for diagnostic tests. And also, those who are working on diagnostic tests, they are not trying to involve process like chemical process or enzymatic process when they implement a diagnostic. And what we got to show you today is to show you how important is chemistry in setting up a diagnostic test. For the background, Drame is here. Drame, come on. Okay, if you take the case in the world, as you can read, many people in the world suffer of dementia. And this is very easy to know, to understand, because with the aging phenomenon, and people are getting older, older. And dementia represents an important factor when we count deaths. And this Alzheimer's disease is the major component to contribute to the death. And this is the same. This is the same trend also in the United States, because with the lifestyles they are getting older. They are getting older, and also I think we get more than 6 million who are suffering of dementia, and each year this rate is increasing. I think you can read the text here. Okay. This is the background. Okay. And Alzheimer's disease is a very complex disease, and also it is a multifactorial disease. It means that there is many etiopathogenetic factors which are involved. Among them, there are genetics. Even many people, many researchers are talking genetics, the role of gene in Alzheimer's disease, but for me, I don't think so. Why? Because for me, genes are modified upon the environment. And other factors is the defect of mitochondrial. Other factors is the oxidative stress. I mean, among all of these, I think oxidative stress play a key role on the installation of Alzheimer's disease. Okay. I will let you read because I have some vision problem. Okay. Now, let's talk about the concepts. The concepts to set up the diagnostics test. Okay. Let you read. Okay. As you see, the free radical species are the nervous system generate contain a lot of radical ions, and because the brain contains lot of metal transition, and the brain also consumes a lot of oxygen, as in the form of superoxide ion, and also the brain contains a lot of lipids, such as the unsaturated lipid, and when we compare this component with other tissues, I mean, to get higher hydroxyl radicals is possibly is probable. Okay, I will let you read.
Excuse me. I'm sorry. So what happened in the brain? In the brain, the superoxide ion is transformed into hydrogen peroxide, and this involves enzyme like superoxide dismutase. Another hypothesis is that the Frampton reaction is occurred. It means it comes up from the reaction between ferrous ions and also the hydrogen peroxide to allow hydroxy radicals. And also the ferrous ions is oxidized to ferric ion. Another possibility of generation of hydroxy ion is the Haber-Weiss reaction between the superoxide anion and also the formed hydroxy peroxide. As you see, in these conditions, there are lots of generation of hydroxy peroxide. And also, the brain, among the neurosteroids, pregnenolone is the most important neurosteroid. And in this condition, pregnenolone here, in the presence of hydroxy radicals, are converted to DHEA. I am not going to go deeply in the mechanism of the reaction, and it comes up. There is an interaction, a strong interaction between the hydrogen and also the hydroxy radical. And the pregnenolone is supposed to get a reaction like a tautomerism. This makes the hydrogen very labile. Okay. Now let's talk about material and method. This is the reaction that we use. I think I am going quickly because there are technical stuff. Okay. 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 So, if I summarize, to get a specific and selective method, we use 3 methods. The first is the radioimmunoassay.
And you know how this method is very sensitive. And we set up the method of the method of quantification of the DAA, the DHEA, and also the pregnenolone. And after that, we use an HPLC. More precisely, is a reverse phase liquid chromatography, which allows us to separate many neurocells, including the DHA, the pregnenolone, hydroxypregnenolone, and some metabolites from the neurosteroids. And in this condition, we fully validate the method. And after, we are recovering the fraction. We get the fraction in which, after many procedures to eliminate the solvent, to extract, to eliminate the solvent, we perform a gas chromatography to a mass spectrum. I will show you. Here, we get here a spectrum of the DHA, and I think you have the parent fragment, okay, which we get around 360, and also other specific fragments, like the higher one, which is located 129, and other specific fragments, okay, like here. Okay, this is the parent fragment, and this is another one. This is another one. Okay. Now let's talk about the results and also the discussion. I told you that this methodology we use allow us to have specific and selective data. Here, as you see, this is a correlation between two methods, the radioimmunoassay method and also the gas chromatography coupled to mass spectrum. And this is a positive correlation. Okay. And here, after, we have a typical chromatogram. This is gas chromatogram for controls with and without ferrous ions. And here we have a chromatogram from AD serum of bucillin, with and without added exogenous ferrous ion. Okay. And the table depicts some data, some demographic data, as you see in the table, the mean plus or minus the standard deviation, showing that the samples are different when we use statistical test. Okay. When we perform the techniques into our samples from blood, we have this shape of results. I think in blue show the positive response, the increase of the amount of DHA in the control A. In green, you have the decrease reaction. This is the same also for the AB control, in which we have increase and also decrease. But if we made a statistical test, we show that patients who are exhibiting an increase are different to those who exhibit a decrease. And the same test is performed with the AB. Okay, in this table, this is important. From the result, you can see when you consider the row corresponding to the age match group, the controls, you see that a proportion of 71.4% of positive. It means there is an increase of the DHA. And 8.9, we have a decrease. And when we perform this technique in the sample of AD, we obtain 33.3% of positive examples which exhibit an increase, and 66% for samples who exhibit a decrease. This is the broad data that we obtain. But when we convert it in a 2-by-2 condensed table, it means this is the method usually used for the diagnostic. We obtain from the controls 71%, and for the negatives, which we call false negative, I think 28.9, and in the second row, who are corresponding to the AD, we get 33.5. This is false positive, and also 66.6, which are false negative. And below, we explain you what is the definitions of these terms. And from the data, we will get the sensitivity of the methods, which is calculated by this formula, and the sensitivity is 66.7%. The selectivity is 71.4%, and the positive predictive value is 71.4%, and the negative predictive value is 76.7. Okay? It means that this method, this methodology is very specific. And what is the problem? Maybe it is not sufficiently sensitive. I think in the development, I will show you what we plan to do to improve, to increase this rate. Okay. And also, when we try to link the clinical criteria, which is the minimal stage examination that usually psychiatrists use to examine the patient, we notice that there is a link between these two criteria. And here, we can, this table show us the results that we get among the AD patients. It shows that there are, I think, 57% of false positive. This is need to be increased. Okay. Okay. In conclusion, this is the characteristics of the method, and it allows us to trace the receiving operating curve, the EROSE curve. This is very important to know what diagnostic is sensitive, is specific, like that. And also, if you have changed some data, you can superpose, you can make a supervision between these two curves, and from that, you can conclude if this diagnostic is more useful than another. Okay. Okay. These results confirm the importance of oxidative stress in the methodology of the diagnostic approach of Alzheimer's, and particularly underline the implication of steroids, because brain are very rich of neurosteroids. Okay. What we plan to do to improve our techniques? First, we gonna follow the advice of Professor Gloria. I think she's here. Effectively, CAM is trying, and we're gonna continue to try. Sorry. And also, this is that what we learned about Professor Kemal. Okay, now in summarize, the AD is a multifactorial disease, and the serum biomarker does not really reflect the whole mechanisms and processes implicated in the pathogenesis of Alzheimer's. In view of the results, the different mechanisms, it seems logical to extend the effort by combination this approach to other parameters. And also to increase the sensitivity and the specificity of the method. We have a choice to combine this approach with other parameters, okay, like alpha chymotrypsin, which is very used as an anti-inflammatory. Or we can use another approach, which I call a etiological approach. The etiological approach may explore other biochemical parameters or other biological targets. And what we consider the feature, we consider the feature by establishing a partnership and also searching, obviously, a financial support, because to my knowledge, there is no publication about a diagnostic antemortem for Alzheimer. And this diagnostic is not a post-mortem. And this method is a non-invasive method to diagnostic Alzheimer. Why? This financial support. Because what we obtained, it is from a sample of 29 patients, and which are divided in two groups: the age match group that we take as a control, and also the AD, the patient who are suffering from Alzheimer's disease. And if we get this support, we're gonna work in better and also well-controlled conditions, because there is a lot of variability which we suspect sometimes when we get this result. The second is to explore other chemical or biochemical parameters or other biological targets, or we make a combination with the etiological approach. Okay. And as we see, with this condition, we have a sensitivity around 66, a specificity around 71, predictive positive value around 71, and also a negative predictive value around 66. And I think, and I strongly believe that if we implement the ecological based approach, okay, we will improve the sensitivity, because we're gonna increase the true positive. And when we increase the true positive, by the way, we're gonna improve also the specificity of the method. Okay. Okay. We're gonna improve the specificity of the method, and also we're gonna improve the positive predictive value, and also we're gonna improve the negative predictive value. I think this will be original, and this will be gonna be very useful for people who are getting older. I really appreciate your attention, and I will say you thank you. And I apologize because I have some vision problems. And if you have any comments, if you have any questions, I'm
Okay. Thank you very much, Dr. Sair Jallow. Now, it's time for the question. Is there any question for Dr. Sair Jallow? No question. Okay, many claps and many thanks for. Okay.